today's video, we'll be covering firstly the interference phenomena, and second part, we'll be covering the electromagnetic spectrum. So I know most of you studied the electromagnetic spectrum already. However, we'll get into much more in depth today, and maybe for some of you, it'll be a refresher. For others, it might be a more in-depth video on what electromagnetic wave is. So if you haven't watched the last video, I'll quickly go over this introduction, right? If you did, you can just use this timestamp in the description and skip to the next section. So how to use this course. So as I said, this is video 1 of 7 on the European Baccalaureate Physics course, and the lecture notes will be available in the video description below on a Google Drive. And after each chapter, in order to solve everything more efficiently and to revise more efficiently, I want you to solve all the exercises that we're going to cover in this video today, and then solve all the past paper questions that is related, and that which I will put in the Google Drive as well, and make a definition sheet of the most important definitions which I'll talk about in this video. So quickly, just to cover, who am I? So I sat the European Baccalaureate in 2025, so this period last year, and I did it in southern France. It's a small town called Manosque, and it's a type 2 European school. You can search that up if you are curious what that is. It's basically a European school that has accredited to teach European Baccalaureate. And as you can see, I did fairly well on the final exam. And on my written examination, I had an overall of 100 in my physics and 95 for my grade point average, and I had an overall of around 97. So topic 1 is going to be the interference phenomena. And as I mentioned in the last video, we're going to be studying these two equations here. We'll learn how to derive them, we'll learn what each quantity mean, and we'll learn what the difference between these two are. And in the second part of this video, we're going to cover the electromagnetic spectrum. And as you can see, I'm sure many of you studied this in S6 as well. And we're going to study it in more detail in how to answer in exams, and we're going to cover example question on what electromagnetic wave question could be. So as you can see, this is an official this is from the official documentation that you can search up. If you search a European Baccalaureate S7 syllabus, you're gonna get around a really long PDF, and from the PDF I screenshotted this, and this is what we're gonna cover today, and this is what we have to cover about the interference phenomena. As you can see, it's one of the two formulas that is covered up here, and then we'll, by the end of this class, you should be able to explain the qualitatively the spread of the wave around the obstacle through the gap using Huygens principle and its dependence on wavelength. Explain the pattern of minima and maxima in the double-slit experiment. Plan, carry out, analyze double-slit experiment in order to simulate process of scientific work and thinking, and derive formulas, which are these two formulas here, and discuss the limitations and the approximations used. Right? By the end of the class, you should be able to do all of it. And then I'm going to discuss this in more detail in the second part of the video, but just to state, right, you just have to know here, and I'll get into more detail later. So I mentioned this in the last part of the video, at the end of the video, but I'm going to go over it again because I emphasized its importance, because as I mentioned last time, that your presentation supposedly is 14% of your final mark when the written examiner is correct. And if you make the examiners happy, right, they're supposed to be unbiased, right? They shouldn't have biases. But at the end of the day, when they're correcting 50, 100 exams, they're all human, right? They're not gonna bother trying to read your messy handwriting if that's their 30th hour correcting the same paper. So we want to make everything as easy and as clean for the examiner to look at, and this is the general framework that our teacher told us to use. And now it's normally 5 steps for success, as my teacher likes to call it, but I added a 0th step, and the 0th step, I call it read the question carefully. Like, read the question fully, because I know a lot of people rush in answering questions. Even, I'm not only talking about baccalaureate, I'm not only talking about just um, physics. It's for every single subject, I feel like. Not only for chemistry, not only for biology, but every subject. You always should read the question fully. Make sure you understand what each words mean, and make sure what you know you've been asked for. And that's why you should write down, right, what you're asked for, right? For example, okay, it's say it's question B, for part 4, right? And you should write down, okay, finding the wavelength. For example, if you're asked to find wavelength, you should write it down so that you don't constantly have to look on paper to see what you're asked to find. Because, okay, that's like 5 seconds that you're gonna do, but if you do that maybe once or twice per question, right? And let's say there are hundreds of questions in total, that's 500 seconds, and that's gonna be almost 10 minutes that you're gonna lose in exams just by not writing this. You're gonna think you're gonna lose time by writing this, but I trust me, you're gonna gain time by always writing the statement and write down the law or formula. This could be, for example, Newton's second law, F is ma. Or maybe for this chapter, you're going to use maybe one of the formulas up here, right? But most of the time for this chapter, you're not going to write down the formula itself, but you're going to be asked to derive. And derivation question, it's 3 points, right? You should always know because it's just memorization. So, and then it's literal calculation, right? Literal calculation means rearranging the formula, right? Without plugging in, for example, the numerical value, right? All the constant values. You just algebraically maneuver and algebraically, yeah, maneuver all the symbols in order to get, for example, if you're asked to find wavelength, you want to find a wavelength in terms of all the quantities that you're given in the question. And 4, it's present with numerical, it's numerical application, and only at the end should you plug in the numbers. You should never ever plug in the numbers while you're doing the literal calculation, right? You don't want to get any intermediate value. You don't want to find anything you're not given to find. Okay, like you found the speed of light, right? For example, right? But you're asked to find a wavelength. Okay, they are related quantities, but you're not really asked to find anything, but you found that value. So what's the point, right? You're just gonna mess up your significant figures, which I'm gonna get into in one of the videos. And uh yeah, never ever, as I said, right? Um plug in the numbers before the last step, okay, before you get the final equation. And then always use a calculator because, okay, it's sometimes simple, right? You can cancel out, you can do some mental calculation. But if you do that over and over again, right, you are going to make mistakes. We aren't like these prodigies who can calculate. If you look on YouTube, and these are like human calculators who can calculate basically any multiplication, division, anything, right? And we're all humans, we make mistakes, right? We're not human calculators, so we can use calculator. So why make it harder for us by not using it? And I don't have the calculator on me right now, but for us, we use the, I think, TI 82 or 83 Python edition. But in this course, I'll be using my TI Inspire because, firstly, I think I lost my TI 80, well, my TI Python edition. So normally, I don't think TI Inspire is allowed, but I'm going to keep emphasizing in this series the importance of knowing your calculator because it will allow you to type down everything faster. You're not going to be searching for any quantity, right? And yeah, I think that's really important. And lastly, 5th step is presenting with units, and we're gonna cover this, right? All these steps. I'm gonna try to follow the steps every time I solve a question so that you can see how I approach it, right? And always present with units. What do I mean, right? It's just, okay, like if the question is asked to find wavelength, you should put that in meters or nanometers. If you're asked to find how long, you should put that in time, right? Seconds. So always present your results with the units that is appropriate. Okay, finally, let's get into the meat of this content. And chapter one is obviously, as I mentioned in the last video, it's going to be waves and oscillation. And I'm sure some of you studied waves and oscillation in the last chapter, and you can try to recall what did you study, right? And the only useful concept that you kind of need is, okay, what is a wave? What are different types of a wave? You don't even really need to know what the different types of waves are, and also what the superposition phenomena states. But we're going to study everything. If you don't know what I'm talking about, it's completely fine. I'm going to cover everything. So, okay. So, so this is one of the important definitions that you should know is, I do not know how to pronounce this guy's name, Huygens-Fresnel principle. That's what I call it. But I watched some YouTube video long ago and they pronounce it Huygen or something like that. I don't know. I think this is a French guy or something, or yeah, I should know. I lived in France, but it's all right. So what this principle states is that each point of a wavefront serves as a source of a new wave, which is called a secondary wavelet. These wavelets have the same frequency and the speed as the original wave and are spherical waves. These overlap and interfere of these secondary wavelets to make up the wavefront at a later time. Okay, that's a mouthful, right? What does this all bullshit mean? Oh, sorry, maybe I shouldn't swear. Okay, what does all these words, confusing words, mean? Okay, and these diagrams may not help at first, but I'll try to explain my best, right? At first, it took me a while to understand what this concept meant. And imagine, okay, you drop a rock in a river, okay? There's a calm water, right? And then you drop, let's say, a piece of rock in the middle. What are you going to observe? You're going to observe these concentric rings that is gonna ripple out at the calm source of water, right? And what this principle states is that actually, like when waves are spreading, right? For instance, okay, let's only study this half of the sphere, right? Okay, there is this part too, but it's easier to imagine just the half, right? Each of these wave fronts consist of little infinitesimal, right? Little wavelets, right? Which they themselves produce little wave fronts. Again, the secondary wave fronts, right? Okay, why is this useful, right? What happens is that each of these points produce their own wave fronts, and these wave fronts interfere constructively in order to build a new wave front, right? And each of these points, right, as you can see, right? Okay, how is a straight wave formed, right? Imagine um, you're on the ocean and you see, for example, a smooth wave coming, right? Like a wave that is, okay, I didn't mean to do that. Wave that is straight, like this, right? I'm not sure if you can see what I'm writing, right? Wave that is straight, like this. Okay, how are these formed? Think for 1 second. How do you think these are formed? Okay, you can see it's quite obvious with the hint given here. But as I mentioned, right, each wave front has a wavelet, right? Each of these points serve as a new source of wave, right? They're spherical, right? But how do these add up to a straight line? Simple, superposition principle, right? They superpose, right? They interfere, right? With this wave interferes with this one, and this one interferes with this one, and so on with all the waves down here, right? And then through this interference, right, what are they going to create? They're going to create a thing that looks like a straight line, right? But if you, and with maybe these type of wavelets, maybe it's not going to look like a straight line, but it's going to maybe look like this. But imagine you have infinitely many wavelets, right? You have millions and millions and millions and millions, because they're not realistically this big, right? You have millions and billions of wavelets, and it's gonna basically look straight, right? So that's why, um, that's how a straight, right, wavefront is formed. And I explained with the spherical one, right? And again, this is an important definition which you should know and you should write down somewhere you want to. And you're gonna find all the lecture materials on the Google Doc below, so you can access that and write down later. Okay, so let me ask you a question. You can pause the video and on a piece of paper, or if you're following this on an iPad or something, although I highly recommend doing all your exercises on paper because the examination is done on paper, which is something I'll mention maybe in a future video as well. But you should always practice the exam in the medium that it's going to be in, right? For example, if you're familiar with the SAT, right, there's the paper and the digital version, right? You're not going to be practicing using the paper version for the digital edition, right? Same here, right? You don't want to be, right, you don't want to get, oh, sorry, you don't want to get used to writing with, like, for example, Apple Pencil on a tablet, right? Because these Apple Pencils are really convenient, right? You can write, you can erase, but in the exam, you're not going to have these convenience, right? What I notice with myself, because in university I only use my tablet, is that sometimes I double tap my normal pencil thinking that it's going to do the eraser feature, right? So it's not always like that. So always, okay, this may not apply to everyone, but if you're using a tablet, I highly suggest you use a paper, right? That's all I studied with in high school, paper and laptop, right? I looked, and normally I like to print out my questions too. So, okay, sidetrack aside, what would you observe, right? Aperture, right? Just to give you a definition, is a small opening, right? In a in a that a wavefront can approach, right? Okay, imagine these are ocean waves. Maybe these are sound waves that are approaching these. It's approaching like maybe a door, maybe a small narrowing, right? Okay, what would happen with these waves? I'll give you 3 seconds, and or you can pause the video to continue, right? I'll give you the answer now if you pause the video, right? What happens is that these waves actually spread out, right? They're gonna keep the same frequency, by the way. So I'm not the best artist in the world, as you can see. That's why I'm in STEM, not in humanities, right? They're gonna kind of look like Wi-Fi symbols, right? And they're going to basically diverge out, right? They're gonna spread, right? And maybe encounter this phenomena, right? And for instance, right, it's like when you hear a person, right, and say that this is a sound wave, someone shouts at you from here, and if you're standing like behind a wall here, you're still gonna hear them, and that is because the sound wave spread out after encountering an aperture. Okay, when an incident plane, right, this is a plane of wave, right, uh, encounters an aperture, each of the point of the incident wavefront acts as a secondary wavelet. However, only the wavelet that are not obstructed by the side of the aperture, uh, yeah, so what that means, right? Okay, let's go back to Huygens-Fresnel principle, okay? And this was this part here. Why does it spread out? If you think about it, is it like it wants to spread out? No, they don't think, right? It doesn't choose to spread out. And this is due to the Huygens-Fresnel principle, right? If you imagine, right? Okay, there is this wavelet that approaches here, right? The wavefront that approaches. And what do we say these wavefronts were actually? They consist of little sources of wavelets, right? So what are they gonna do? Right? The middle ones, right? They're gonna just interfere normally, right? As I said with the example with this one up here, right? They're just gonna interfere into a straight line, right? But however, look what is gonna happen to the ones at the edge, okay? Okay, let me draw them here so that I can actually 1 second. Let me draw them in the middle so that it's more clear. Right in the middle, they're just gonna interfere to create a straight line. Make sense? All right, that's what I explained in the concept before. So if you didn't understand, watch again. Right. However, the ones out here at the edge are obstructed by an aperture, right? By a wall. What are they gonna do? Right? what they're gonna do is basically, um, I mean, when they encounter here, right, they're still gonna spread out, right? But here, they don't have anything, right? The wavelets here, right, they just hit a wall, so they can't interfere with the waves here, so they're just gonna act as a new wavelet, right? They're gonna here act as a new wavelet, right? And that is because they don't have any wavelets here because it has been obstructed by a wall, as you can see. They have it obstructed, right? So that's why the waves at the edge, right? Here, wavelets at the edge, they don't interfere, right? So the edges, right? Although down here they interfere and they make a straight line, right? That's why the waves, right? They spread out in a manner that is, yeah, they diverge out, basically. That's what I'm trying to say, right? I hope that explanation is clear, right? The reason is because of the Huygens-Fresnel principle. Why they spread out? Because the waves at the edge, they do not have anything to interfere with on top, or like top up here, or if it's the case down here, they don't have anything to interfere with here, right? So they still spread out because Huygens-Fresnel principle states that each point in a wavefront acts as a where does it say? Serves as a force of new waves and these have same frequency original waves and are spherical, right? Each of the wave fronts, each of the points here are spherical, right? And they interfere eventually in order to create a straight line, some odd shape, right? But however here they have it obstructed, so they cannot create a straight, or they cannot create their original shape. That's why they look spherical. Okay, so let's look at the concept down here, right? Okay, this I'll cover after covering this page here, right? Okay, and what do you think, right? If you imagine these wavelets, right? These wavefronts have the same, let's say the wavelength, right? They have the same wavelength and they're in the same medium, right? The only difference is between these two are the aperture length, right? As you can clearly see, right? The one on the right is clearly bigger than the one on the left. So which one is going to diffract more, right? Diffract meaning that, okay, which one is gonna have a larger angle of spreading out, right? That's what it means. Do you think one that is smaller is gonna have a larger angle, or is the one bigger going to have a larger angle, right? I'll let you pause the video here and try to figure it out yourself. Assuming you pause the video and try to figure out yourself, the answer is that smaller aperture, right, has a larger diffraction angle, meaning that bigger aperture must have a bigger angle, right? For example, let's call this some arbitrary degree, right? We're not given the value. Let's say that this is 60 degrees, and let's say that that's maybe 30 degrees, right? So as you can see, smaller the aperture, smaller the angle, right? No, well, that's technically the case, right? Smaller the angle, but when we're technically, I made a mistake here. When we're technically talking about the angle, we only talk about the angle that makes up this, right? I'm not sure if you can see properly, but we actually talk about this angle here, how much it spreads out here, right? So if you draw a line here, right? So technically this, you see, this angle here, and if you compare to this, the angle on the left is, as you can see, much bigger than the angle on the right. So therefore, smaller aperture, right? Smaller aperture results in a larger diffraction angle, right? So we can write this relation as, okay, let's call this aperture A, and we said that they have an inverse proportion, right? And let's call this theta. And we can also write down from this property here that also theta is inversely proportional to the aperture. And this is the relation we have up here, right? And And why do we have lambda here, right? It's not going to be a scientific proof. It's not going to be any derivation or anything, but I'm just going to give you an intuition, okay? When you zoom into a wave, right? It's kind of the same thing as, right? Changing the wavelength, right? As you can see, maybe on the screen, it's going to be perhaps if you're watching on a monitor, maybe it's like 5 centimeters. But when you zoom out, maybe it's 1 centimeter now on your screen, right? And proportionally, right, if you look at it, you can look at it as same thing as just changing the wavelength, right? So bigger the wavelength, bigger the angle of um, diffraction is going to be. Diffraction, diffraction, I don't know how most people pronounce that, but it's it's almost like you're zooming into the wave and trying to make the wave look bigger, right? So bigger wave, right, means a bigger angle. So I know at first it's fairly non-intuitive, but um, I'm trying to think of a way just to explain it better than just zooming in analogy. But mm, let me think. Yeah, I think zooming in analogy explains it fairly well, right? Let's say that yeah. So so the so the proportionality is that the angle of incidence is directly proportional to the wavelength, and angle of not incident angle of diffraction is directly proportional to 1 over a, or inversely proportional to 1 over aperture. So if you combine this, right, you can get that theta is lambda over a, right? And that's the thing we got up there, right? And this is the answer of how we answered here, right? And as you can see, as the slit or aperture decreases, the diffraction increases. What does this mean? So as a, right, the aperture gets smaller, right? Gets smaller, right? This means not smaller than zero, right? Like this decreases, right? This means that the angle, diffraction angle, increases, meaning that they if if one increases and the other decreases, it means they have an inverse proportionality, right? Okay, I think when trying to understand these concepts, it's good really to have a solid understanding of the history of light. And we're going to get into much more detail when we're studying quantum physics, and also when we're studying the history of light. But I would like to mention the history of light to kind of understand why all of these are significant. You all know Newton from S6 and way before, right? He's scientist, philosopher, or basically everything, who discovered many things, right? The modern calculus, the modern mathematics, maybe not modern mathematics, but modern calculus and modern physics, right? Oh, you know the Newton's three laws, right? And he's a really famous person, and he stated that light, in fact, right, like visible light, the light you see up here, the sunlight, those kind of visible lights are particles, because he observed that when he shines the light through a prism, he observes a rainbow. Thus, he concluded that, okay, so lights consist of these different colored particles. That's not exactly what he said, but it gets a good understanding, right? Um, Different colored particles. That's why they spread out like the diagram here. And later, right, around, I guess, 200, almost 200 years later, a scientist called Thomas Young, and he's a key figure in this chapter because we're going to study Young's double-slit experiment, right? He's the Thomas Young, right? And he did what we call an um, interference experiment, the double-slit experiment, in order to quote unquote prove that light was a wave, or technically, to put it more precisely, that light had a wave-like property. And what James Maxwell, and if you study if you go electrical engineering, you're gonna hate this guy, right? Because uh, well, you will see eventually, right? So basically, what James Maxwell, this prodigy and genius, proved is that actually the visible lights are electromagnetic waves, right? And if something is a wave, it obviously means that it has wave. It is a wave, right? So by proving that visible light belongs to the electromagnetic spectrum, for example, um, radio waves, microwaves, infrared light, all these X-rays, gamma rays, right, and visible light was just in between the infrared and the ultraviolet light. That's what he sort of proved, right? And then here comes Einstein in 1905, who says actually light is also has, I mean, to put it more precisely, has a particle um, property, meaning his famous, what we call, maybe some of you have heard of it, right? Which we will also study as well, his photoelectric effect. You don't need to know what that means, but using that experiment, he proved that light had, in fact, um, particle-like properties as Newton stated, right? So how does it happen? Okay, Newton, particle. That's what he believed. Thomas Young and James Maxwell, they believed wave, right? That light is a wave. Albert Einstein, he's like, actually, uh, light is both, right? That's why he proved, because they have a particle property and a wave property, and this is in modern physics or in quantum physics, I believe. I'm not a quantum physicist. I'm just still a university student, so I don't have the authorities to say perhaps. But this is why we say light has particle wave duality. We'll study this later as well in the chapter 6 or 7. And right now, I read some modern research, and they're talking about how light exists, the photons to be more precise, exist in a Higgs field or something. I don't know what that means. So, as you can see, science is constantly evolving, right? So, um, this story is important because it allows us to understand why Thomas Young's experiment is significant, and also later in the chapter, why Albert Einstein's photoelectric effect was also very significant. Okay, imagine, right? There is a double slit. Okay, what is a double slit? It's just slit, right? Is okay. Imagine this is a card, right? And imagine there's a slit in a piece of paper, right? This is a slit. Okay, what is a double slit? If you guessed it right, double slit is when there are two slits, right? And imagine through this double slit, let's say this is a very small distance, right? Uh maybe less than a millimeter even, right? Imagine you shine a laser light through it, right? As you can see on the diagram here on the left, right? Imagine you shine a laser through here. What do you think you're going to observe on the other side, right? Imagine you shine the laser, and back here you have like a screen. What pattern do you think you're going to observe on the screen here? You can pause the video, you can try to guess it yourself, or if you don't want to, we can just carry on with the video. So, what we're actually going to observe, right? Okay, let's separate that into two scenarios, okay? Let's separate that into Newton's theory that light is a particle, and maybe let's split that into Thomas Young's theory that light is in fact a wave, right? What do you think you're going to observe if light is a particle, right? On the screen, which is going to be maybe two spots of bright spots, right? That's what you're going to observe, perhaps, right? If light was a particle, right? I mean, this is what we experience with shadows, right? I mean, if there are, um, if you imagine maybe a jail cell, right? And light is coming through the jail cell bars, you're not gonna observe any other pattern than the shadows of the bars, right? So that is our first intuition. However, um, what we actually end up observing, as you can see here, is going to be many lines instead of one lines from just two slits. Okay, you're going to observe more than one bright spots from two slits. I find that amazing that you can, I mean, what I was really surprised by is that you can still do this experiment at home. All you need is just to get a double slit. I'm sure you can order it online, AliExpress or Amazon, right? And or in school, normally you would do this experiment, right? This is what we did, right? You just put a slit, you shine a laser through it, and you observe what is on the other side. And generally, what you're going to observe is many bright dots, basically. And what does this prove actually, right? This proves that light is actually a wave. Okay, why does it prove that by observing many dots that light is a wave, right? Okay, so yeah, as you can see, this is what you'll actually observe, right, on the screen, right? If you shine a laser through it, right, you see many bright spots and you see regions of dark spots, right? Same on the other side, right? Dark spots and bright spots, right? And they progressively get darker, right? We're going to be able to explain this, right? But just to tell you, okay, why do you think this pattern forms? And if you remember from the beginning of the video that you have to have knowledge of what superposition principle is, right? And yeah, this is just a simplified diagram of what it is, right? Because as you know, right, if light is a wave, that means they diffract, right? That was what we said Huygens-Fresnel principle was, right? That when a wave encounters an aperture, right, they diffract, right? So, but why, right? But as I said, we need to understand what superposition principle is, right? This is an important definition. You should write this down. Superposition principle is when two or more waves overlap in space, the net displacement at any point in the algebraic sum of the individual displacement that each wave would produce on its own, right? It's a mouthful. It's a complicated definition. Definitions, right, don't really tell you because they're really, really dense information uh jumbled into one sentence, right? That's why trying to read definition isn't always the best way of trying to understand stuff because for example on Wikipedia, that's why it's really hard to learn science through Wikipedia because okay, it's good, right? It's really dense in information, but if you're encountering the subject for the first time, you're not going to understand anything in the sentence, you know. That's why um that's why I think studying through YouTube video rather than books or reading articles is more useful because the person can actually explain it to you in your level, right? Okay, what do you remember about the superposition principle? Is that, for example, if you add up these two waves, right? When, for example, there's a peak to peak interference, right? This is peak, right? This is trough, right? Okay, let's say there's a peak to peak interference. What are they going to add up to, right? If they have an amplitude of A, they're going to add up to 2A. That is the algebraic sum part because 1 plus 1 is 2, right? So, uh, as you can see, yeah, for example, okay, let's study another point here. Maybe the 0 point, right? What is 0 plus 0? 0. Perfect, right? What is minus 1 times minus 1 plus minus 1? It is my minus 2, right? Minus 1 plus minus 1 plus minus 1. Yeah, minus 2. I'm sorry if I said minus, no, I'm sorry if I said 0 times 0. I meant 0 plus 0. And if you study any of these points here, right? For example, you study here, here, right? If you add these up, it's gonna maybe be, maybe not there, maybe here, right? So that's what I mean, right? And this is called, right, if they add up to something positive, right, if they have a net positive interference, we call this a constructive interference, right? Or constructive superposition, but I'd like to call it constructive interference because we're studying the interference phenomena, right? Okay, what happens if, okay, you see the answer already, but imagine you didn't see. If you add up the peak and the valley, right? The peak and the trough. If you add those two, right, what do you think happens? Okay, by the way, another word for peak that you might encounter is crest. So just to let you know, right? Okay, imagine this is A and this is a minus A. What is A plus minus A? If you said 0, perfect. It is 0. And if you study any point on this wave, right? If you do maybe minus A here, right? Minus A, and then this point is A, right? You're going to get 0, right? And if you study any point on this wave compared to the same position here, right? Not same position, but I guess, yeah, I guess same position or same time, depends on what is on the x-axis, right? If you study any of these points here and add it up with any of the points here, you're going to get 0. And this is known as destructive interference, right? It makes sense, right? If it adds up to something greater, we call it constructive, right? And if it destroys each other, and so destructive interference. Good way to think about it, right? And good. And as I said, in European Baccalaureate, you're expected to use technical terminology, right? In the exam, if you're asked to maybe explain what the superposition principle is, right? You can't say the high point on the wave, the low point on the wave, the middle point on the wave. You want to be using the technical terms, right? We call it peak or crest. We call it trough, right? Maybe there's another word for trough, but this is generally what I use, trough, right? And this middle position is generally referred to as, and here it's a resting position, or also known as equilibrium position, right? And wavelength, right, is basically how long the wave is before it repeats itself. Imagine there's this module here, right? And then if you repeat this, right, you're going to get another wave, you're going to get another wave, you're going to get another wave, right? So this is what wavelength is. Okay, let's do this quick exercise here, right? Exercise 2 on interference. And I specifically wanted to do question 4 here to talk about the interference principle, the superposition principle, right? And the interference phenomena, right? And if you read the question, two loudspeakers are connected to a signal generator and placed at a position A and B. As shown in figure 1, yeah, this is figure 1, this figure displays the circular wave fronts coming from the loudspeakers, propagating through air. The circles indicate the wave crests. As I said, crest is the high points, right? The wave trough are located between the two consecutive wave crests, right? Obviously makes sense. The wavelength of the sound is 3.4 meter and frequency is 100 hertz, right? Okay, let's study this here. And what question 4 is asking for is determine if it's constructive or destructive interference and the points P, Q, and R. Okay, P, Q, and R, right? P, R, Q. Okay, pause the video right now, right? If you want to try to solve it yourself. If you can't, or if you manage, unpause the video and continue watching. And assuming that you just solved this, let's see if P is constructive or destructive. What did the question state about the circular positions, right? The circles in the diagram, they said that the circles indicate the wave crest, right? So here, as you can see, two wave crests are meeting. What do we say about two wave crest meeting here? We said that it is a constructive interference. So we know that P is a constructive interference. Right now, I'm not going to do the complete justification for each, how you should write it, right? The 5 steps for success, right? Because I don't want you to think about multiple things at once. For now, I just want you to understand what superposition principle is. Okay, what is Q then, right? Q, right, is, as you can see, right in between the two wavelets, two waves of point source B, right? And then it is on the crest of A, okay? How do we know it is on, for B, that it is a wave trough, right? How do we know that it's a trough, not a crest? You know that the wave troughs are located in between, right in the middle of the two consecutive crests, right? So here should be, right, a destructive interference. Why? Because B is at the bottom position and A is at the top position, which means that they add up to 0, right? So that's why Q is destructive. And R, right, as you can see, right, we know that R is in the crest of point source B, right? And R is in trough of source A. Again, this must be then destructive as well. Right? If you haven't fully understood the concept of constructive and destructive, I recommend trying to go back a couple minutes before I solve this question, read it again, and trying solving it again after watching this part one more time. And there is no shame in doing that. It takes many practices in order to become good at something, right? For me, I'm going to side tangent a bit again, but I think if I heard someone say this to me, I would find it useful, right? That you will never pick up something on your first try, right? Like, although, like, okay, like I did score really good in every single class exams, right? When I was in class actually listening to what the teacher was saying, half the time I was sitting and I was like, what is that symbol the teacher wrote on the board? You know, what I'm telling you is that if you don't understand anything in class, it's okay, right? If you just put in the time, right? I think this is what a lot of people mistake, is that people think people are good at math or physics or chemistry is that, oh, they're just genius, right? Okay, there are some exceptions, right? There are real geniuses, but in my case, it was that I just put in the time and effort and trying to understand every single minute details, right? For me, I used, my time as leverage compared to, people who are just born smart, So, yeah. So, okay, we understood what double slit experiment, not double slit, but we understood what superposition principle is, right? But why did we need the superposition principle for? We need it to explain why we observe these fringes, right? So let's go back to why do we observe these bright spots and dark spots. And when I say fringes, right, I mean, I generally mean, if I say just a fringe, it means I'm generally referring to a bright fringe, and there could be a dark fringe as well. And fringe means just spots or lines of dark or bright regions, right? If you say a bright fringe, I mean by this fringe here. If I mean by a dark fringe, I mean by one right here, right? Just for the vocabulary. And I think this diagram helps understand kind of why um why there are bright spots and dark spots. For example, on the diagram, as you can see, on the bright spot, you see a constructive interference where there is a peak to peak, right, between the orange and blue, right? Orange and blue waves, right? They have peak to peak interference between the light. So that's why there's a bright region, right? And here, right, they have the opposite phase, right? So they have a peak to trough interference which means that they're going to interfere destructively, hence a dark region. Okay, and these bright fringes can be only explained, right, if light have wave properties, because particles, if you imagine, right, don't do this, right? If you imagine, as I said, right, shadows, right, they don't interfere or anything, right, unless the shadows get really, really small, right? But in this scale, right, uh, in this scale, we can only explain the bright and dark fringes through interference of waves, and hence this is why Thomas Young, quote unquote, proved that light was in fact a wave and not a particle through his experiment, right? And I'm gonna kind of explain how he did his experiment later as well, because obviously back then he didn't have a laser, right? So, uh, what this explains is that what double slit experiment proved is that light, in fact, has particle, no, wave-like properties, right? Okay, and as you saw on the formula sheet, way up there, right? I'm not gonna scroll all the way, but these are the two formulas that you have on the formula sheet. And the formula right here is going to be generally the one that you're going to be asked to derive. And to my experience, around 8 out of 10 times, so 4/5 of the time, you are going to be asked for this derivation here, right? And you are going to learn what each of these symbols mean, how you should derive it, how you can become better at deriving it every time, right? For this formula here, right? So this proof is to memorize, okay? And obviously I'm not gonna just throw this at you and expect you to just know everything all at once. No, for me this took me maybe at least 10 tries doing same question over and over again, trying to test myself in areas that I didn't understand, right? In order to prove why this experiment is true, right? Why this, not experiment, but this formula is true. Okay. And okay, let's get into more detail about this proof, right? And this, as you can see here, is actually a scan or picture of my first in-class exam, not my baccalaureate, but I still have my baccalaureate. But I thought this was more clear, right? This was actually what I did in exam, right? And I think it's fairly clean the way I presented it, right? As you can see, right? Right? I did write down step number 1, right? Writing down the question, right? And then I did step number 2, right? Writing down the assumptions or, well, the laws, right? In this case, there isn't any law, but yeah. And then I did my literal calculation, right? And in this question, I didn't need to do numerical calculation. That's why I stopped here, right? And then I presented my results down here, right? So the first part, when it comes to when you're asked to prove the formula here, right, is going to be drawing your diagrams, right? And I'll show you like a typical question in a baccalaureate exam, okay? This is from 2013, no, not 2013, 2019 baccalaureate, right? Show stating the approximation used that the position of the maxima on the screen is given by the formula here, which I told you is basically this formula here, but a bit rearranged, right? So as I said, right, you're not going to be actually using this formula that often, right? All you're going to be asked to do is derive the formula here. I would say 8 of the 10 cases, or actually 9 out of the 10 cases. Okay, I'm going to explain you the derivation. Ah, it's hard talking to a camera for an hour straight. I don't know how some YouTubers do it. Okay, so where was I? Okay, so I said that step 1 is drawing a simplified diagram of this experiment because it's gonna make it clear for the examiner as well as yourself that you do know what you're doing. Okay, this is how I drew my experiment. Okay, and generally when you're drawing this, you don't have to draw all of these experiments to scale. Okay, as you can see on my left hand side, this is my double slit. As you can see here, right? These are my slits, right? And this is my slit distance, which I called S, right? And what we're actually assuming, right? We don't really care about, it took me a while to realize, about actually the size of the slit itself. Let me take a better pen. We don't actually care about this size, but all we care about when we mention this, the slit size, double slit size, is the distance between the center of each slit. That's all we care about. We don't care about anything else when it comes to the slit distance S, or maybe you're going to be given small d, but let's keep it for S for now. Okay. Imagine, right, through this slit, right, you shine a laser through it, right? Okay. You shine a laser through it or some source of light, right? And imagine, right? Let me go up here, right? Let's assume that there is a constructed interference at some arbitrary zone, right? Up here, right? Let's say that there is a zone of constructive interference up here. Let's just say that it's a zone of constructive interference, right? And let's say that, let's call this value xn, right? It's the nth bright spot, right? That's what we're assuming. There could be xn minus 1th, right? There could be xn plus 1th, right? But what we're just assuming is that, okay, let's just say that the point here, up here, is just going to be xnth bright fringe. And let's assume as well that, okay, there's a lot of assumption going on, but I'm going to tell you the assumptions that you have to write down here, right? And then say that, okay, imagine there's a beam of light coming from here because, okay, it's technically not a beam of light. There are wave fronts, right? That is diverging, right? And then there is another wavefront coming from here, right? And you can kind of think of this as a beam as well. That is converging as well, right? And then imagine on this spot is a construct interference because it's a crest to crest interference, right? And if you imagine, right, there might be a crest, maybe with this one, right? Maybe there's another wavefront here. Maybe there's a crest to trough interference perhaps here, right? Maybe that's why you see a dark fringe here. But let's just assume that the point here, the xnth bright fringe, is a constructed interference. In other words, it's a crest to crest or peak to peak interference, right? Superposition, the same thing, interference, superposition, right? Let me clean up a bit. And then we can just simplify this by saying that instead of you drawing all the wavefronts because it gets really, really messy, let's just draw them as beam of lights here, okay? And what we can also assume is, and let's draw an approximate line that is from the middle of the diagram, right, to the diagram, right, to the point where it hits the wall, okay? And then let's call this angle theta, right? And this is important, okay? And uh, and then we can also call this angle theta as well, right? And okay, you might ask yourself, actually, why are these two angles equal, right? They don't even look like similar triangles, right? Because if you imagine the big triangle here, right, which I highlighted in cyan, I believe, what that, is that cyan? Well, light blue, right? If you imagine this triangle here, and then if you imagine the small purple triangle there, right? They don't necessarily have to be equal, right? That's the thing. These are, okay, let me redraw. Okay. These don't necessarily look like similar triangles, right? But these are actually similar triangles because of what we're assuming, okay? And I told you actually that we are not drawing this diagram to scale, right? If you really, really zoomed in on the slit, right? What we're gonna actually see is that the rays, right? Itself, right? The light beams, right? These ones, right? Are actually gonna basically look almost parallel, right? In this diagram, it doesn't look parallel because it's not to scale. But if you imagine that this distance itself, the d, the distance between the big D, this is what we call it, right? The capital D, right? If we assume that this distance is much, much larger than the slit distance, right? This is our first assumption here. I'll explain much more later, but we have to understand the assumption in order to understand the drawing. So it's going to get involved, right? It's going to require a lot of wrapping your head around things, right? And don't worry if you're not getting this first try. I told you it took me at least 10 tries to get this, right? I'm going to give you much more opportunities to practice yourself, compare it against my answers, right? And if you imagine, right, that if you really, really zoom into the slits, right, it's the two rays are basically going to look parallel, right? And they're going to share probably the same angle here, right? Theta and theta, right? And then as we said, if we draw like another one here, like a little line in the middle in between, just so that we can assume that um that's kind of like an approximation of the angle here as well. And we can also say that this is theta as well, right? These are the same angle, right? And then imagine we draw this line down here, right? And then if you imagine, right, okay, these waves continue maybe for like a couple more meters, right? The distance here is going to be the difference between the two wavelengths. Okay, what does that mean, right? As I said, as I said, right, this point xn is a zone of constructive interference, meaning that they add up positively, right? They have a constructive interference, meaning that this is a peak to peak or trough to trough interference, right? So what could this mean? This means that either the waves, let's say that there are two waves here. If you duplicate, okay, if you duplicate this, right? Say that you add these up together. Let's do the same exercise. What are you gonna get? You're gonna get same thing, but larger in amplitude, right? Imagine you actually shift this value by around this much here, okay? And then if you imagine, right, what are you gonna get? You're gonna get a destructive interference, right? But say that you actually nudged it a bit more. What are you gonna get? You're gonna get a constructive interference again, right? So what am I trying to prove with this diagram here is that if the wave, if the phase of the wave is shifted by its wavelength, right? If it's shifted by its wavelength, right? This is its wavelength, right? If it's shifted by one wavelength, it means that they can constructively interfere again, right? So, uh, so this could be, for example, the phase difference here, right? We call that just a random symbol, right? We call that uh, delta, right? And we call this um, integer multiple of wavelength. Okay, I'm going to explain why a bit more later as well. But in order to understand the equality of this triangle of why the blue triangle and the purple triangle are equal, right? It requires you to understand that if you zoom in enough, that these angles look very similar, and you can assume that they're very similar. And one of the consequences of this assumption is that the theta here and here is the same, right? How Okay, and this is going to be your basic diagram here. You can memorize the exact one I drew, or you can draw perhaps the diagram here, right? And I think this is a much better diagram, to be honest, but it's more complicated to draw in my opinion. So I wouldn't necessarily recommend drawing this, but as you can see, right, if you actually zoom in to the waves, right, and for example, this is distance d, right, but as you can see the ripple lines here, it means that a long distance in between has been cut off, right, some certain distance, the squiggly lines here, right? So by this assumption that these two angles are equal, we can say that this angle as well is equal, right? And don't worry again if this doesn't make sense to you right away, right? We're going to cover this again. So, as I said, you're going to need to state two assumptions. And we technically did many assumptions before, but these are the two assumptions that the examiners expect you to write, and they are kind of the same thing as what I said, just phrased a little more coherently and more simple. First assumption you're going to make is that the distance between the slit and the screen is very different. Okay, for example, the distance between the screen, right, and the slit is, let's say, 10 meters, and this distance here is maybe 0.0001 meter, right? So they're in orders of magnitudes different, right? Maybe 10 to the 10 to the power 5 times different, right? So what I'm saying is that by assuming that the distance between the slit and the screen and the distance between the two slits, right, are very large, we can assume that the two rays coming from the slits can be considered parallel. This is what I explained, right? By assuming that these rays, in fact, are parallel, right? And whereas in reality, this doesn't really make sense, right? If you have two straight lines, how are they going to meet, right? Because if we're assuming that they're actually converging into a one point on the diagram here, right? It technically doesn't really make sense, right? Okay, how are they straight, have the same angle, but eventually converge? It doesn't make sense, right? But what we have to notice is that perhaps maybe this angle might be 29.9995 degrees, and this itself could be maybe 29.9994 degrees, right? For instance, right, we're in the questions, you're never going to be given angles, but I'm just saying for you to understand, right? They may have slightly very small difference in angle, but we can assume that they're so similar, right? Because the distance between the screen and the slit and the distance between the two slits are very in orders of magnitude different, right? 10 to the power of 5 or more different, right? It's not necessarily 10 to the power of 5, but it's generally around that distance, I would imagine. Maybe 10 to the power of 3 to 10 to the power of 5 orders of magnitudes different, right? Under that assumption, we can say that the two incoming rays are parallel, which means that this angle theta and this angle's as well theta. Second assumption we're going to make is that the since the screen is very, very far away, we can assume that theta is almost zero, right? It seems like we're doing witchcraft, right? We're saying, okay, the theta, the two different angles are actually the same, and now we're saying the two different angles are zero. What is that supposed to mean? Okay, say that you have the screen here, right? Say that there's a slit, and you say that there's a slit, and you have two slits here, right? And then maybe you have the screen here, right? Maybe the screen is here, and let's say that this is the middle, right? Say that this is the middle, right, of the two slits. And imagine that this is the setup here. This is the double slit, and then this is the wall, right? This is the screen that you're going to be observing the thing at, right? The interference pattern at. And say that perhaps, right, as I mentioned yesterday, that theta in reality is very, very small. And in under like standard laboratory condition, for instance, right, we're gonna see that um, if the distance between the screen and the slit, right, is let's say 2 meters, and the slit difference, right? I did some research here. Slit length, let's say it's around 0.25 millimeters, and apparently, right, I mean, we can't derive it yet because we haven't found the full formula, but if we do some simple calculations, which you should be able to do later, right? The theta is approximately like 0.145 degrees, right? And grand scheme of things, this is a very, very small angle, right? Like even 1 degree is very small. And imagine like 0.145 degrees, right? And although I wrote that, okay, theta is approximately zero, right? I think it's always better to write, okay, theta is smaller than 1 degree, right? And I made a table here, as you can see. If there's a difference in this table, it's because I did a new table because the one before was quite confusing. So I think this one was better, right? And on the left hand side, you see the angle in degrees, right? In increments of 0.1 degrees. And then you see the sine function here, and you see the tangent function here. And what you can observe is that, okay, at 0, 0, they're all equal, right? This and this is equal. But we see that, okay, 0.1 degree, right? This is approximately the standard laboratory condition angle, right? Maybe 0.1 and 0.2 degrees, right? You can see that sine and tangent are practically equal to within four significant figures. You can see that for 0.2 degrees, they're practically equal to. For 0.3 degrees, they're equal again. 0.4, they're equal to. 0.5, they're equal as well, right? And then you can see until okay, 0.7 degrees, it's where they start to diverge a bit, right? More than, let's say, I would say that's more than four significant figures, right? But what you can see is that even for 10 degrees, right, they're similar within two significant figure, right? So we can see that for angles smaller than 1 degree, they're accurate within four or more significant figure, because here we're just displaying four significant figure, but in reality they could be equal to more significant figures, right? More numbers here. So for very, very small angle, right, you can visualize this too. Maybe if you know open GeoGebra or Desmos, depending on what your favorite online calculator is. If you zoom in to the center, right, you see the sine function, right? This is a sine function, and you know that tan function, for instance, is kind of, I mean, not the best artist in the world, right? Kind of like this, right? If you zoom in, zoom in, and zoom in, and if you're, let's say, between 0 degrees and 1 degree, right, we're gonna observe that they're practically just straight line, right? That are basically equal to each other, right? So they will obviously diverge more as tan approaches infinity, but for very, very small angle between 1 degree, right? 0 and 1 degree, they're practically equal, as you can see, right? And that's what we can say, right? Because the screen is very far, theta is very small. And therefore, we can work under the assumption that sine is equal to tan, or approximately equal. And this is going to lend us a very useful result and through the consequences, right? And okay, let me just erase this because I continued till here yesterday, but I decided to cut this part out because I think I seemed way too tired and I was just blabbing random things. So we know that, as I mentioned, that this phase difference, right? Imagine that these two rays are the same length, right? They're parallel as well. That's what we're assuming. Okay, they're technically not parallel, but you know, let's say that these are okay. We just do that one more time, duplicate, and then let me just shift this by maybe this degrees, right? Okay, say that they are practically equal, right? This distance is equal to two distances. Let's say that this distance here is equal to this distance here, right? You know that, as I said, if you shift the wave, right, you can get a constructive interference, right? I'm sure, I don't know if you remember, but or maybe you learned it in a S6, but I do remember learning about the periodicity of sine and cosine functions, right? Because you know that sine function is 2 pi periodic. You know that cos is also 2 pi periodic, and you know that tan is pi periodic, right? And let's say that there are so you know that sine function and cos and tan are always periodic, they repeat, right? And we can always scale that up, scale that down depending on the size that we want. But okay, imagine that there are waves here, right? Okay, but the waves are in reality much smaller, right? In the realms of nanometers, right? Right, and then here is a constructive interference, so it's either peak to peak or trough to trough, right? So the only two difference between these two waves, right, because they come in at the same phase, right, is going to be the distance here, right? And this is what we call the phase difference. It's how much we shift the first and the second wave by, right? And this phase distance is going to be important, right? And okay, let's just call from this triangle here, right? You know that it's a right angle triangle. Let's call the bottom side, right? Um, delta, it's a lowercase delta, and then the hypotenuse is going to be s. Okay, it's getting too crowded. So what I like to do when drawing this is just enlarge the triangle, right? I just colored it using the highlighter. Okay, you know the triangle one is the same purple triangle on the left hand side as well as the right hand side, right? So you know that this is the phase difference and that we call just delta, and the slit difference, right? Slit size is we call S, right? And in actual exam, they might use different symbols. Maybe for this instead they use D, and or maybe they use L, right? But just symbols are symbols. So just keep in mind if you're rewatching this video while solving another one, right? That it is always the same, right? Just different symbols, right? And you know that under the first assumption, we got the result that these angles are equal, right? Since the two rays are parallel, this means that the angles are equal, right? Okay, what can we know? How can we write down the relationship between uh between S? Okay, this does not look like S. It looks like a delta. S and delta, right? If we know the angle here. And using basic trigonometry, we can state that sine of theta is going to be equal to the opposite over hypotenuse, right? So we know this relationship here using the first triangle, right? That's what we said, right? Using triangle one, right? Triangle one is what I drew here, right? We can say that sine of theta is going to be delta, the phase difference, over the slit difference S, right? And I said that the second assumption is important, right? And as I said, that the consequence of the second assumption is that sine theta is equal to tan theta, right? Okay, how is this related? You may ask, but we can say on the screen, the second triangle, we know that this angle is also equal to theta, and you know that we can just draw a right angle triangle here, just saying, okay, we can draw like a right angle triangle, right? You know that this part is a center between the two slits, right? And you know that this is right angle here, I already drew that. And you know that this angle here, again, is theta. I wrote it, but I'm writing it down again. And as I said, this distance is xn, and you know that this length is d, right? Okay, let me just make that a bit more clear, right? Just drawing that triangle again using the same colors so that it's not too crowded, right? Okay, and then you know that this length here is xn, this is theta, this is d. Okay, how can we relate these two quantities here? If you use trigonometry, we can say tan of theta is going to be opposite over adjacent, right? And you know that under you can say that, okay, using this triangle here, I wrote triangle 2 is this one, right? Triangle 2. We can say that tan of theta is going to be this height here, right? This is the opposite over adjacent. Okay, what do we say about the second consequence, right? Second assumption's consequence, we know that sine theta is equal to tan theta. In other words, you know that the value here, right? Sine theta is equal to tan theta, which means that delta over S is equal to xn over d, right? This is what we're gonna write here, right? I mean, I haven't written down that yet, but we can say from that step here that xn over d is delta over S because sine theta is basically equal to tan theta, right? That makes sense, right? This, right, is the same, and you know that this is the same. So, yeah, here I'm just zooming in again. I think I put this slide just so that you can have a look at it one more time, right? Just writing down the assumption, and yeah. Okay, so what do we mention about the bright fringe, right? About the spot that is here, right? The xn position. We mentioned that the position, right, xn is, we said that we're assuming that is a constructive interference, meaning that it's a zone of constructive interference. Makes sense, right? We under the assumption that that zone is a constructive interference, right? I wrote here, xn is a bright fringe, which implies that it's a point of constructive interference. And as I mentioned, sine function, right, or cos function, they are periodic, meaning that they repeat every 2 pi, right? And instead of saying, okay, sine repeats every 2 pi, for a wave, we can say a wavelength, right? They're periodic, right? Every wavelength, right? I mean, it's very obvious, right? This is the wavelength, right? This distance here is wavelength. And if you repeat this wavelength, right? Okay, let me just make this a bit bigger, right? You get a periodic wave, right? So what I'm trying to say, or what I'm trying to let you understand, is that if there is an integer, or if there's a whole number difference between the phase difference, right? if the phase difference here, right, is equal to a whole number multiple, let's say 1 wavelength, 2 wavelength, 3 wavelength, right? It means that these zones are going to be constructive interference, right? So as I wrote here, you should always justify when writing this. Since it is given that the waves are coherent and have the same frequency, the phase difference delta should be an integer multiple of the wavelength, right? So there, I mean, it's a mouthful, but just to explain it briefly, right? You know that since the zone here, xn, is a point of constructive interference, you know that the phase difference delta must be a whole number wavelength difference, right? Delta n, or yeah, it should be a whole number difference of the wavelength. Does it make sense, right? I hope that makes sense. And we can express thus the delta as a whole number multiple of the wavelength delta of the wavelength, yeah, of the wavelength, right? So we can say that, okay, the wavelength is any integer, meaning, okay, it's like -2, -1, 0, 1, 2, dot, 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 the other way. And if you write this in a very fancy mathematical rigorous notation, it can say n is a set, is a element in integer, right? That's what this means. This z here, right, with 2 lines in the middle, means it's an integer, right? An integer is just a whole number including 0 and negative numbers, right? That's what integer is. All right. And you can say that, okay, so you know that sine, right, theta is sine theta, we got that it was delta over s, right? But since we laid out that delta is actually equal to n times lambda, you can just write that down, right? Where n is just a integer, right? N is an element of an integer, right? So under this assumption that, this was a second assumption, I'm just going in a different order I wrote here than what I explained, but it is the same thing, right? We can say that, okay, this sine here, right, is equal to this, right? The sine is equal to this, and you know that tangent, right, this value here, as I said, was equal to this, right? Or, well, it's the same thing here, right? Equal to this, right? And we can thus say that n times lambda over s is going to be equal to xn times d, right? Xn, not times d, but xn over d. Okay, and we can do a quick rearrangement of formula here. I can say that xn is equal to n lambda d time over all over s, right? We can just multiply d on both sides, and we're going to get this formula down here, right? And this is the first part of proof that is done, right? And this is what you're going to be generally asked for in exam, as I told you down here, right? It's going to be the thing that we have to find here, but this one is just with different symbols, right? Instead of d, it's L. Instead of lambda, instead of n, it's k, right? Instead of small d, it's a, right? It's just different symbols that you're going to be asked in exam, but exactly the same framework that you're going to apply, right? Exactly the same method of proof, right? And then sometimes you might be asked to find what delta x is, right? And what delta x is, right, is, well, it's the same thing as this formula, whereas here it's just delta y, but I wrote instead of delta x because that was given in the question, right? But delta x and delta y is different, is the same thing, because we're just stating, right? We could have written this as yn, but in the question it said to use xn, so that's why I use xn instead of yn. It's just different symbols that we're gonna replace, right? It's just placeholder, right? That's what it is. All it is a placeholder. And you know that delta in general is going to be, okay, if you think of delta x is generally the final position minus initial position, right? But since here we don't really have final and initial, how are we supposed to approach it, right? And we can kind of think of this in terms of series. If you learned what series is, right, is n plus 1th term minus nth term, right? Or you can just say xn minus xn minus 1. These two, right, are gonna yield you the exact same results because it's just gonna cancel out everything. However, I decided to do xn plus 1 minus xn, right, because they yield the same thing and they should give us the difference between the position xn plus 1 and xn, right? What does that mean, right? I told you that the position here is xn, right? And there might be xn minus 1 position here, and there might be xn minus 2, and there might be the 0th position here, right? And then up here, we're saying this is xn, and then up here, there might be xn plus 1th position here. That's what it is, just bright spots that we're assuming, right? And we're trying to find the difference, right, here. And this is going to be delta x, right? And delta x is equal between every single bright spots or the zone of constructive interference. So we can say that xn plus 1, right, is just going to be n plus 1 times delta times wavelength times d over s, right? Because we're just replacing n with n plus 1, right? And then here we just write the n because it's not any special term, just n. And then we can write this down as n times lambda times d over all over s, right? And what do we notice? We can collect like terms, right? We can just factorize by lambda d over s, right? That's what I did. I factorized by lambda d over s. And what do we do when we factorize? We just collect the terms here and collect the terms here. Okay, it's going to be n plus 1. Don't forget the minus sign. Going to be minus n, right? And you know that you see that the n's cancel out, that leaving you with 1, and anything times 1 is itself. So we're just going to get lambda times d over s, and this is what the result that we wanted, which is delta x, right? And okay, if the question asks you to derive like this, which you're generally not going to ask for, but okay, we found that delta x is going to be lambda d over s, and we can just rewrite this as delta x over d is lambda over s, right? It is exactly the same formula, and I hope by now you sort of understood how to approach how this proof works. We're gonna go over it together again. If you don't understand, don't worry, but yeah, we're gonna cover an actual question right here, so don't worry. And for now, we're not going to get too deep into the electromagnetic spectrum, but just as a refresher, right? Try to state the electromagnetic spectrum if you haven't looked at it yet in order, right? I want you to write it in terms of the shortest wavelength to the longest wavelength, right? So here, if you draw an arrow here, right? The lambda is smallest here, and the lambda is largest here, right? It's a big lambda, right? So I'll pause the video now, write down the electromagnetic spectrum, right? We want to be doing active recall. Assuming that you wrote down the electromagnetic spectrum on a piece of paper or recited in your head, the shortest wavelength is one with the highest energy, and you know that that is gamma, right? Gamma, you can write gamma rays, or you can write, actually spell it out, say gamma rays. What's after gamma? There is X-rays. And then after X-rays, you know that there is UV, right? Or ultraviolet light. And then you know that there's visible light. Uh, visible light. And then you know that there is infrared light, or IR light. IR light. And after IR, you know that there is microwave. And then the longest one is radio waves, right? And this is the order we should know, right? If if you're given to state an order of shortest frequency to longest frequency, the list, right, would be flipped, right? Wait, shortest frequency. Okay, I do not recall what I said, but if you're given, let's say, the longest frequency here, right, to the shortest, the list must be flipped, right? Because you know that lambda is inversely proportional to frequency, right? And you know that lambda is just equal to c over f, right? Where c stands for speed of light, right? Okay, let's cover this question together. This was the exercise. This was a question in the 2019 baccalaureate. And we will be solving this together. Okay, so if you want, you can pause the video now, try to solve it yourself, and then try to compare your results with mine. Assuming that you paused the video and did it, let's continue. Okay, so we always want to follow the five step approach framework, right? 5 steps for success, as like my teacher likes to call it. And as I always told you, step 0, read the question. Student performed Young's experiment using laser light with wavelength lambda. Okay. The light is incident on a double slit with slit separation A. An interference pattern is observed on a screen located at the distance L from the double slit. The screen is parallel to the plane of the double slits. Okay. So how will we do this? Right? Okay, imagine this is one of the questions. I will be writing down one, right? First part of the question, and the first part of the question is to prove this formula here, right? Show stating the approximation used, important stating the approximation used, that the position of the maxima on the screen is given by xk is equal to k times L times lambda all over A, where k is a integer, right? You know that you should always write down the statement, what you're going to find. So for this one, I'll just simply write proof of xk k over L lambda over A, where k belongs to an integer, right? Because I want to save time. I don't want to be writing down 0 plus or minus 1 plus or minus 2 dot dot dot, right? I'm just trying to save time much as possible, right? Then if you remember the proof, what do we always start with? We start off using a diagram, right? Okay, you know that there's double slit. Oh, let's draw a double slit on here. Okay, I'm gonna use a thicker pen and okay, see that there's a double slit here, right? And then this double slit has a slit separation of A, right? And then you know that the screen is located L from the double slit. Okay, let's say that this distance here is L. Okay, and you know that the wavelength is lambda, and that's all the things that are given, right? Okay, so let's assume that around here is the middle of the two slits, and you say that you're going to observe a maxima on this point here, right? Okay, let's say that these two rays come out, creating a maxima at that point right there. Okay, and it's called the first ray, since it's at top, let's call that ray 1, and let's call this ray 2. Okay, I'm going to take a thinner pen, right? And you know that you can also just say that these two rays, right, have the same angle, right? That's the first assumption that we're going to write down, right? And you know that through that assumption, you know that this is going to be equal as well, right? This is the same theta that we mentioned about. And you know that we are going to call this distance what? We're not going to call it xn, but in this case, the variable is k, so we're going to just call it xk. Okay. Okay, this is what we're given, right? And just continue the line here. And you know that this is right angle as well, right? Okay, so as I said, the first assumption that you're going to make, okay, and you want to write this down very explicitly. You don't want the examiner to be searching for it because they literally asked you, state the approximations used, right? Okay, let's state assumption 1. We said that the slit size A is much, much smaller than the distance between the slit and the screen, right? We're assuming this. This was our first assumption, if you remember, which I wrote here, right? And we can say, since these, right, A and L have a very big difference, we can say, so ray 1 and ray 2 can be assumed as being parallel to each other. Right? And the second assumption that we're going to make, right? Assumption numero 2, right? Number 2, as I mentioned, is that screen is very far away. So the theta is smaller than 1 degree, or we can say theta is very small. You can say theta smaller than 1 degrees, right? And the consequence of this assumption was that sine theta is basically equal to tan theta, right? That's what we assumed. So let's say that let's call this triangle here, right? We want to make this clear for the examiner as well, right? We want to say, okay, that is too big. Okay, we know that there's this triangle here, and we also know that there is another triangle here. It is laggy. You know that there's another triangle here. Like this, right? And let's just call this one triangle 1. Let's call this triangle 2. Okay, let's say using triangle 1, we can state that you know that the triangle 1, right? I'll just redraw it for you guys here. You can redraw it or not redraw it during the exam, but it's really up to you, right? That was A, and you know that this is phase difference delta, and you know that this angle is theta. So we can state that sine of theta is actually equal to delta over the slit separation A, right? Using triangle 2, which is the big triangle, that is the green one, we can state that tan of theta is going to be equal to opposite over adjacent, right? So it's going to be xk over L, right? So it's, and we initially assume that this zone here, right, the pink zone here, is a zone of constructive interference, right? So we must write that down. Assuming that xk is a zone of constructive interference, the phase difference delta must be an integer multiple of the wavelength, right? And we can express this as delta is equal to k times lambda, where k is equal to 0, plus or minus 1, plus or minus 2, etc., right? Or we can just say just k belongs to a natural number, right? Not natural number, my bad. Must be integer, right? Okay, what is the next step? The next step is combining these questions, right? From assumption number 2, which states that tan of theta is equal to sine of theta, this implies that you know that tan of theta is xk over L, and you know that sine of theta is delta over A. Okay. And which also means that n lambda over A, right? We're just replacing this with n lambda over A, which we found here, right? No, not n, k lambda over L, right? So by rearranging this formula, we can get that xk by multiplying L on both sides, right? You can say that xk is gonna be k lambda L over A, right? When we can just rearrange this to write k L lambda over A, which should be the same thing as what we wrote up there, or what is in the question, right? Where k is 0, plus or minus 1, plus or minus 2, etc. Right? This is the first proof done, right? And I don't know how long exactly I took to do this, maybe a bit more than 10 minutes, but if you repeat this maybe 10, 20 times, you should be able to do this proof under 5 minutes. This, if you get this question on an exam, this should be a free point. Like this is something you should not get wrong on an exam. Okay, let's continue with question number 2, right? Part 2. Knowing that the distance between the third order maxima on the screen is 3.6 centimeters and L is equal to 4 meters, right? I think they forgot to write meters here. And lambda is equal to 546 nanometers. calculate the slit separation A. See figure below. Okay, let's say, okay, this is x0, right? And you know that the next one should be x1, the one after should be x2, and then now we have x3, right? So you know that x nth value is given by the distance between the 0 value and the x nth value, right? If you observe it on the screen, right? Say that there's maxima here, that is the middle, right? There's a maxima in the middle. The first maxima, second, and the third. The distance is measured by this, and what we're saying is that there is this distance here, right? Between x equals x3 and x minus 3 is 3.6 centimeters. In other words, this distance here must be 1.8 centimeters, right? So, question 2, we want to finding slit separation A, right? That's what we're trying to find. So, we want to put what we wrote here into words, right? So we can write, we know that the distance between n equals 3, well actually it's not n, right? It's k equals 3 and k equals minus 3 is 3.6 centimeters. Therefore, the distance between k equals 3 and k equals 0 must be 3.6 centimeter divided by 2, which is 1.8 centimeter, right? We put what we said up there into words, right? Okay, we are given quantities, and now we want to find slit separation A, right? Okay, what are we given, right? We derived the formula, xk is equal to k lambda L over A, correct? Right? From part A, part 1, right? So this implies that A slit separation is equal to k times lambda A L over xk, right? Just basic algebra manipulation, right? And since we're given the values for k, right? You know that k is 3. You know that lambda is 546 nanometers. And L is equal to, I think, 4 meters. And you know the xk was 1.8 centimeters, right? So by plugging that in, right? Now we're doing the numerical application part. That is part 4, if I remember correctly. You know that k is 3. 3 times, you know that the wavelength is 546 nanometers. So 546 times 10 to the power of minus 9. Because that's what nano stands for, right? 10 to the power of minus 9. And you know that L is equal to 1.8 centimeters or 0.018 meters, right? And you know that xk is equal to, oh my bad, L is not equal to that. L was equal to 4 meters, and you know the xk is equal to, yeah, 0.018 meters, right? If you put this into the calculator, so as I was saying, if you put this value into the calculator, this is the value you're going to get. As I said in the last video, right, I lost my other TI 83 Python edition, I believe. I'm currently using the TI Inspire, which just a heads up again, you should always practice with your own calculator in order to get good at your calculator, because you don't want to be practicing with, you know, like other tools, because you want to save time during the exam. You know, you want to know each and every button where it is. It should come from your muscle memory, right? So it's just one advice that you should always use your own calculator and try to become good at using your calculator to its 100% full potential, right? And always double check if you inputted the right values. And for me, I get the slit separation for part A must be equal to 3.64 times 10 to the power of minus 4. What should be the unit for A? Should be meters, right? Okay, let's continue with part 3. Okay, using a double slit with A is equal to 3.64 times 10 to the power minus 4 meter, the student replaces, which is exactly the value we got for some reason, right? So which I think also shows that we probably got the right answer, which emits a red light, lambda is equal to 672 nanometers, and green light, lambda 2. On the screen, there is an overlap of interference patterns. A maximum for green overlaps with a third order maximum for red. Determine the wavelength lambda 2 of the green light and the order maximum overlapping the red and the order of the green maximum overlapping the red maximum. Okay, so let's try to visualize this first, okay? So basically the situation is that, okay, we have a double slit here. Let me just take a thicker pen. There's a double slit here. And what we're doing, we're shooting two types of lasers, right? We're shooting a green laser, right? Which means a red laser, and then a green light, right? There is green, and then let's take a red pen. There's a red, right? Lambda 1, right? Red light here. Okay, so on the wall, what are we going to observe? So basically, the third maxima for red, right? If I believe, yeah, third maxima for red. So it should be, this is 0th, 1st, 2nd, 3rd, right? Overlaps with a green maximum, right? So green, where is green? Okay, overlaps with the green maximum. Let's say this one overlaps with the green maximum, so I'll draw one. Oh, deletes. Okay, that's, imagine these two overlap when you shoot red laser through here, right? And then if you also shoot green laser through here, right? And but we don't necessarily know what the nth maximum for the red laser is, right? No, the green laser is. We know that for red laser, right? X3, right? Because it's the third maxima, right? You know that this one is X2, this one is X1, and X0. But most likely, right? Here is what we can assume. We know initially that we learned from the beginning of the lesson that the angle of diffraction is directly proportional to the wavelength. Or, as we wrote it simply, angle of diffraction was lambda over the slit length, right? We know that this slit length is a constant, so we can say that, okay, since we know this relation, we can also state that the larger the wavelength, the larger the angle that it is going to diffract, right? But we know that the green wavelength is necessarily smaller than the red wavelength. Why is that? If you look at the electromagnetic spectrum of the visible region, this is why it's important to memorize the visible. This is why it's important to memorize the visible region. Is because if you look at the visible region, it's going to start off with, right? Say that this is increasing wavelength, right? You know that the shortest wavelength is violet, right? Not purple, violet. These are two different colors. I mean, they're the same thing. One refers to a more scientific terminology. The other refers to a more, I guess, artistic terminology. And then there is sort of bluish. There is greenish. There is, and then yellowish. There is, I mean, I don't have orange here, but there is orangish and then reddish at the longest wavelength, right? So necessarily, right, from this here, we can see that red has a longer wavelength than green, right? So green has a shorter wavelength. Also, you know that green is a higher energy, right? So here's what we know, right? So what could this mean, right? This could also imply that since these two quantities are directly proportional, that the angle that the green diffracts is smaller than the angle that the red diffracts in, right? Does that make sense? So necessarily, right, this here should be where n is larger than 3, right? Because green diffracts less, right? So maybe green's third maxima in reality is here, and maybe this is perhaps its fourth maxima. But we're not given that yet, right? So it could be n is equal to 3, 4, 5, right? But it's larger than 3. I think I said 3, right? It's from 4, 5, 6, right? Those are the acceptable values, right? This is a situation drawn. You don't have to draw this in an exam, obviously. This was just to explain to you how you should approach this problem. So, okay, in reality, you should write here. What are we looking for? So we're finding lambda green and n, right? Let's say that's just an nth value, okay? Okay, so first step is that, so recall that in part 1, we derived this relation here, right? Okay, I can just copy paste this here, right? I'll just copy paste this relation here, copy. Okay, but that is not the copy function, right? Let's just not duplicate, copy, and then let's just paste, right? We know this equality is true. So this implies that for the green wavelength, right? For the green, so as I was saying, that this implies for the green wavelength that for green, let's say that it is going to be lambda k times lambda green, right? Let's just call that lambda g times L all over A, right? Aperture A. Whereas for red wavelength, this implies that it is going to be, so we know that k is its third maxima. So that k is equal to 3. So 3 times lambda red, just call that lambda r times L all over A. And we know that this maxima here, the green maxima, let's call that x green, and then the red maxima are overlapping, meaning that they are equal, right? So let's put these two equal, okay? And then this is equal to this, right? This is what the equality implies. So, okay, what do we notice on both sides immediately? That, okay, A is a constant, cancels out. You know that L is a constant, cancels out. So what does this imply? Simply, this implies that K times the wavelength of green is equal to 3 times lambda times R, right? Okay, so technically we are missing two variables here, right? Two unknowns, because we don't know K, we don't know we don't know lambda of the wavelength of the green wave. However, what we can do is assume that, okay, let's just assume that k is greater than 3, right? Let's say lambda green is going to be 3 over k times lambda red, right? This is what, right? We just divided both sides by k. Let's assume that k is larger than, not 0, 3. So what is the next whole number that comes after 3? This implies, so let k is equal to 4. This implies that the lambda green is going to be 3/4 of the lambda red. And you know that the wavelength of the red light given here is 672 nanometers. So it's going to be 3 over 4 times 672 nanometers. So if you just punch this into your calculator, so 3/4 of 672, 4 over times 672 must equal 504 nanometers. Okay, technically, K can be 5 as well. Let's explore the case when K is 5. Okay, you know that the green could be 3/5 of lambda times wavelength, so you know that's 3/5 times 672 nanometers, right? So let's just multiply that by 3/5, which is equal to 430.2 nanometers. Okay, 432 nanometers if we count that to three significant figure, right? Because we know that's given in three significant figures, so we must answer in three significant figures, right? Okay, when K is equal to 5, we get 403 nanometers, and when K is equal to 4, we know that's 504 nanometers, right? However, we're given that it is a green light. If you look at the visible spectrum, as I explained here, violet is approximately 350 to around 400 nanometers. Should you know this? Yes, you should. You should know that around the violet region, it's around 400 nanometers, right? 350 to 400 nanometer is the maximum that the human can observe, the smallest wavelength the human observe. And the longest wavelength that human can observe is around, let's say 700, okay, like more like 650 to 750, depending on the person, right? So we know that the green light is probably somewhere in the middle, right? If you look at your rainbow between violet and red, right? So it's probably around the 500 region, sorry, 500, between 500 and 600 region. So what is closer to 500? Obviously, when K is equal to 4. Sorry, we can justify since it is given that the light is green, K must equal 4, and thus lambda of green must equal 504 nanometers, right? Full justification, and I hope I explained everything correctly, fairly intuitively for this question here, right? Okay, so we'll be moving on to the second part of this chapter, which is gonna be the diffraction, doesn't matter how you pronounce it, grating. So while you drink water, have a think of it this question. If there's more than two slits, right? You know that traditionally there are, what we study is two slits, right? What happens if there is actually three slits maybe, right? 1, 2, 3, or maybe 4, right? 1, 2, 3, 4, right? I drew this one wrong. What do you think will happen if there's more than one slits? More than two slits, I mean. I know if you think it's weird, I'm transferring from my bottle to my cup, but I have a really big bottle, that's why. Plus, the bottle keeps the water nice and cold. So do you think A, it all cancels out? 2, a new pattern emerged? 3, nothing happens. So in reality, right, you may think, okay, it might cancel out. There might be more interference, and then these all might cancel out. Well, fair enough, right? It could happen, but it doesn't. Nothing changes. Could be true, right? Maybe, okay, these two act as one interference, these two act as another interference, and they just, nothing changes, right? Perhaps. Or a new pattern emerges, and the real answer is somewhere in between 2 and 3, right? So what really happens is, as the number of slits increase, right? As you can see there, this is what happens if there's 2 slits. This is what happens if there are 3 slits. This is what happens if there are 4 slits, right? So basically, right, each of the bright spots become exponentially, right? Not exponentially, but by, I believe, uh, the number of slits squared. That's what I believe, but you don't have to know this. This is what I realized when I was doing my research, right? So they increase a lot, right? When there's 2 slits, okay, maybe the intensity is here. When there's 3 slits, the intensity basically doubled. And when there are 4 slits, the intensity basically quadrupled, right? So this is how they increase, and this is what you would observe actually on the screen, right? Each of the dots actually get brighter, and they, as you can see, they spread out much less, right? They're concentrated in a smaller area compared to the double slit experiment where it's quite broad, right? Because because technically here is a zone of maximal constructive interference. Here maybe it's like constructive interference, but like not by much. And here is the total destructive interference, right? So as you can see, the constructive interference zone becomes larger in amplitude, right? And then we can just ignore this part because this part you really don't have to explain in the European Baccalaureate, right? So as we can see, as there is more and more slits, each of the intensity spots gets more and more defined and more intense, right? Okay, you know that 2 slits, right? This is what we said we'll observe, right? These bright fringes. But as there's more and more fringes, as I said, there's going to be brighter and brighter spots, right? So why is this the case, right? Why is it the case that when there's more and more slits, that the bright spots become brighter, right? If you think this through a bit, it might become very trivial, it might become very obvious. And that is because, right, each part becomes brighter simply because there is more source of light coming from it, right? Imagine, right, instead of 2 lasers coming here, 2 rays coming here, there are now 4, 5, 6, 7, 8, 10, or 20 lasers pointing at the same spot, right? So that's why each individual spot, right, become brighter, right? So this is a slightly important definition to know. If you're asked what is a diffraction grating, grating is a grating with a periodic structure of appropriate scale so as to diffract light. So the definition might sound circular because we're using grating and grating here, but you know that grating, like a cheese grater, for example, right, it has a periodic structure, meaning that it has a consistent structure, right? For instance, okay, there might be a constant gap, right? Always constant, right? S, 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 and S. I know this isn't the best drawing, but bear with me here, right? Maybe this is grating with a constant distance S, right? That is in the scale so that diffracts light, right? And it's important that it is in scale because, for instance, when the light comes through your door, right, or your window, it doesn't diffract, right? It only diffracts or diffracts when the wavelength, when the aperture itself is actually comparable, right, to the wavelength, right? You know that the visible light is, let's take it broad. Let's say around 400 nanometers to 700 nanometers for simplicity's sake, right? And these gratings should be in orders of magnitude, maybe 10 times these wavelengths, right? And that is like the maximum size that it can diffract. Because if you like hold your finger like this, right, and then you just try to see the light, right, you're not going to see any diffraction happening, or because it's not a double slit, obviously, first of all. But even if you had maybe just if you hold maybe a paper and then you cut 2 slits at it, you're not going to observe uh, any interference pattern because the slits, right, the slit distance is not small enough. So this is another proof that you'll have to memorize for the European Baccalaureate. And this proof is much, much simpler, right? What the European Baccalaureate expects you from this is not much. All they want is you to draw these 2 diagrams, and these 2 diagrams are actually from the European Baccalaureate correction paper itself. So I don't know what year is this from, but probably 2018 or 2019 paper, right? And this is what they expect you to draw, right? And they're assuming that, okay, this is partially a diffraction grating when we zoom in, right? Because diffraction grating is, as I said, double slit, but like repeated, right? So just imagine there is slits here, 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 here. But let's just, by zooming on just these two slits here, right? That's what we're doing, right? We're just zooming on just two of them, and we're just saying, okay, let's just simply draw them here, right? And we see that in this diagram here, there's a slit difference of d, and then you see that there's a theta n, right? For instance, here, right, they didn't even draw the angles here, right, which are also theta, and they didn't even write down the assumption, because for 99% of your diffraction grating proof that you're going to be asked for, you don't need to write down the assumption unless explicitly stated, right? And this is the first diagram you're going to have to draw, right? You can draw the exact same one, or you can have a look at ones I'm going to draw later in the example that I'm going to give. And this is the second diagram that you're going to have to draw, which is just, okay, imagine this is a grating and we're just too lazy to draw everything. So what we're going to do is just say, okay, there's a grating here, there's a wall here, and if we just zoom out, right, we're going to say, okay, it forms an angle of theta n with d here, and then xn, because this is a zone of constructed interference, as I talked about before. And as you can see, this is very, very similar to the proof for double slit experiment. And I think this is where a lot of people get tripped up, is that they're not the same thing. And if you mix these two formulas, right, you're going to get 0 points, right? Maybe not 0 points, but you're not going to get full points on the question. So never mix the question, right? And generally for diffraction grating, you're going to be actually dealing with angles, right? You're not going to be assuming that tan theta is almost equal to sine theta for this one, right? You're not going to be assuming any of that, right? And you're actually going to be dealing with the sine angle itself, and you'll be able to derive, okay, what will be the angle of the first order? What will be the angle for the second order? What will be the angle for the third order, right? That's what you're generally going to be calculating with the diffraction grating question in the European Baccalaureate. As you can see with the first diagram, as the person wrote it here already for the European Baccalaureate, but he said the tangent of this angle here, right, theta n, is going to be equal to opposite over adjacent, right? Basic trigonometry. And then for this triangle here, we can say that sine of theta n is going to be adjacent, right? We can just say this is lambda n, right? But no, not lambda, my bad. This is going to be path difference over slit distance d, right? And we can, but for this one, you don't even have to write down the assumption that, okay, since xn is a zone, no, since xn is a zone of constructive interference, it means that the phase difference should be an integer multiple of the wavelength. You don't even have to write that down. You can just say, okay, just assume that it is a integer multiple where n is just an integer, right? And I prefer this notation here. I know I'm sidetracking a bit over, let's just say n is equal to 0, 1, 2, 3, blah, blah, blah. And you always have to include plus and minus, right? If you just learn this quick notation here, right, that means n, maybe you learned it already if you took higher level maths and S6. N is an element, or yeah, as n is an element and integer. That's what it all means, right? Nothing too complicated. So from this formula, we can see that, for instance, okay, if we want to find the slit difference, we can find it. Okay, if we want to find the n, right, nth value, we can find it. If you want to find the wavelength, if we're given the angle and the slit distance, we can find that too. So, however, if you want to find, for instance, the angle, any of this, right? For example, I'll get into example later. I think it's too abstract right now, so I will actually not say what I was planning to say. So let's actually try with the question here, okay? So this is part B of question 2. I'm not sure which baccalaureate it is from, but it is from one of the baccalaureate. If you want, you can pause the video now and solve it yourself and come back to the video to solve it together with me. Okay, assuming that you solved the question already, right? Let's go over it together. How should we do? How should we answer the question, right? For the baccalaureate, what it says on the first page is that you should answer each question on a separate page, right? This is question 2. You should take a new page normally. And you should say, okay, this is Q2, right? Right. And then we're doing part A, I. Okay. Okay, what is I asking for? Showed using a label diagram that the separation D between the two consecutive lines on the grating is given by D is equal to n lambda times sine theta n. Okay, so we should say proof of E is equal to n lambda sine theta n, right? So, okay, it's asking for a labeled diagram, right? So if you remember how we did it before, we're gonna just do it the exact same way, right? Okay, assume that this is a grating, right? And then assume that there are maybe two rays coming out of it, okay? And then say, call this distance t, no, not t, but delta. Call this distance t, and we know that this is theta, right? So we can say, so since so we can just, okay, so from the triangle, right, from the right angle triangle, we can deduce the following. You can say that sine of theta, right, since that is a right angle down here, right, we can say sine of theta n, right, because it's technically theta n, is supposed to be gonna be adjacent over hypotenuse, right? Hypotenuse is a t. And let's just write a bit more detail for this question, right? Because okay, it's worth 2 points, so we want to make sure we capture every point, right? But if you're short on time, you don't have to write this. You can say since we are assuming a zone of constructive interference, the phase difference should be a integer multiple of the wavelength, right? When we're using n, not k, right? Where n belongs to an integer, right? Thus, sine n theta is going to be n lambda over d, which is equal to the proof that we need here, so which is equal to the value here, and hence proved, right? Okay, so yep, that is the proof done. I think we'll get full marks for this question, right? Okay, let's try part A, part 2, right? So part 2, showing D is equal to 1.69 micrometers. So we found the formula for D, right? So we can say we found in part 1 that D is equal to n lambda times sine theta n. Okay? So we know the wavelength, right? We know the wavelength here. We know the distance D, and actually we know the distance D, and we know the separation between the central maximum and the first order maximum is 71 centimeters, right? In other words, this distance here is 71 centimeters. So, okay, however, we do not actually have the angle here, right? We do not actually have theta n, right? And what we can do is do some basic trigonometry, right? And this is the second diagram is going to come in handy, right? We saw that from far away, the second diagram basically looked like this, right? You can just say that this is x0 and this is xn, right? And this made an angle, certain angle theta, n, right? And we can say that this is going to be the first order. So let's just say, okay, let's just assume this is the first order, n equals 1. And then this is also going to change, right? You know this distance here is going to be capital D. And then you know that this height here is just x1, right? So we can actually say that, okay, tan of theta 1 is going to be opposite x1 over d. And here we can just deduce that theta 1 is going to be arctangent of x1 over d, right? So we can say that d is going to be n lambda over sine of, right, this value here, right? So you know that n is also equal to 1, so you can just get rid of n, right? You can just say arctan of x1 over d, right? Okay, now let's plug in the values since we know individual everything. So you know that lambda is going to be 420 nanometers, so 420 times 10 to the power minus 9. You know that sine of arc tangent of x1 is 71 centimeters, or in other words, 0.71 meters, right? 0.710, keeping all the significant figures. And then you know that t is 2.77 meters, right? 2.77 meters. What you have to be careful during trigonometry question is always look, is your calculator in radians or in degrees? And most of the times for these questions, you're going to be handling with degrees. So let's go ahead. Okay, my calculator is currently at radians, so that's why you should know how to use your calculator, because if you are not comfortable with your calculator, you're going to waste 15 minutes on the exam trying to change from radians to degrees. So for my calculator, hopefully I remember my way of changing it. Okay, so it's document setting, uh, and then it's radians, switch to degrees. Okay, so now I'm degree mode. It's gonna be 420 to the power of minus 9 over trig sine, over sine of trig of arctangent of 0.71 over 2.77. Okay, and I get a value of 1.6915, so we can just do 3 significant figure times 10 to the power minus 6 meters, right? And then you know that 10 to the power minus 6, this part here is just micro, so we can just say 1.69 times 10 to the power of, no, times micrometers, right? Since micro just stands for this part here, right? So hence proved, right? Okay, let's continue with part 2. No, part 3. Okay, explain whether or not this violet laser can produce a maximum of order n equals 5 using the grating. Okay. Can n equals 5 exist, right? That's a shortened version of the question. So how should we know if n equals 5 should or should not exist? Okay. And we know the formula here, right? And if we know that, okay, I'll just rewrite the formula here, right? From part 1, right? We prove that d is equal to n lambda times sine theta n, right? So here, okay, let's just assume that n equals 5 exists. So here we can say that sine of theta n is going to be theta 5, my bad, is going to be 5 lambda times d, right? And then we can say that 5 lambda is going to be 5 times 420 times 10 to the power minus 9 over d, as we found, was 1.69 micrometers, right? 1.69 micrometers, which is 10 to the power of minus, not 9, but minus 6. So let's plug this into calculator real quick. And I know some teachers recommend, okay, you should cancel out your powers of 10 first, but I don't really recommend doing that actually, because when you're checking your calculator history at the end of the exam, right, to double check your calculation to see if you typed in everything correctly, it's gonna get real confusing. So that's why I don't always recommend doing that, but maybe for you it might work best, but for me it just yielded in me making more errors. So I get a value of, so I get that sine of theta 5 is 1.24, right? Okay, just by looking at this, is this possible, yes or no? Right? And just by looking at this is actually impossible, because theta, right? You know that the range of sine, right? Range of sine of any angle, right, is in between -1 and 1. Sine can never be larger than 1, right? So we can justify saying that since sine of theta, right, is a function whose range is limited to -1 and 1, right? N equals 5, or in other words, theta 5 cannot exist. Thus, n equals 5 is not possible. So this is, for this question, it was a mathematical argument, and it is sufficient. Okay, let's go with part 3 and part 4. So explain without calculation the effect of x1 of using diffraction grating smaller, okay, using a smaller value of d, okay? So, okay, let's just summarize that real quick, right? So effect on x1 if d was smaller, right? That's essentially the question, right? Using a smaller grating, okay. So we know, okay, so we're gonna do a lot of invoking from previous question again. We know that t is equal to n lambda over sine theta n from part 1. So for n equals 1, you can say that t is equal to lambda over sine theta, right? Okay, 1 second. Actually, we need to invoke from question 2. We need this formula here in order to just prove it, right? Okay. Actually, we can just invoke another property. We can just say using diffraction grading smaller, right? So it will be just 1 second. Okay, so I mean, there are multiple ways of going about this, to be honest, but okay, let's go with a more rigorous way, honestly. Okay, so just go back, right? We know this property here, right? And we also know that theta was tan arctangent of x1 over t, right? So we can see that so we can see that d and theta, no, d and x1 can be considered inversely proportional for small angles, right? Because, okay, if you put the theta here, right, and you know that sine is an increasing function, right, for the range that we care about, which is basically 0 to 90 degrees, right? And we know that tan is also increasing for 0 to 90 degrees, right? So we can say this statement here, therefore, decreasing, so yeah, the question up here was, therefore decreasing d will result in a larger x1, right? Simple justification. Okay, so part 5, explain without a calculator the effect of doubling x1, effect on x1 of doubling the distance d from the grating from the screen using the grating with d is equal to, okay, so we know, okay, let's do this quickly here. You know, for this one, part 5, effect on x1 if d doubled. Okay, so we know the relation that okay, if it's the same angle, just 1 second, and effect of doubling d on the grading screen and using the, so if oh yeah, just simple, yeah, just simple. So you know that tan, we derived that tan of theta and is gonna be xn over t, right? And imagine if d is doubled, what is going to be the effect on the xn, right? So that is the question here. And we can just rearrange this by saying, okay, xn is equal to d times tan theta n. And we can say that theta n is a constant if n is a constant, right? Because we are given that the slit difference, slit distance, d, is also a constant. Okay, so you know that tan of theta n must be a constant as well. So we know that xn is directly proportional to d, which implies that doubling d must also double xn, right? Simple justification. So in this case, it was x1, but xn is for the general case, so we can just substitute x1 here in this case. Okay. And okay, let's continue with the rest of the two questions here. And normally you should be able to solve this much quicker than I am, but in the actual exam, you're going to have around 40 minutes for this question. So don't worry too much if you're not able to solve this quickly, but without my yapping, right, you should be able to solve this, I would say, relatively under 20 minutes. Okay, let's continue with B. So the experiment is repeated using the same grating, but the green laser is used. The value D, 2.77 meter, remains unchanged. The angle between the second order maximum and the central maximum is 9.2 degrees greater for green light than for violet light. Calculate the wavelength of the green light. Okay, this is a fairly complicated question, as you can see. 3 points. So we need to title this Calculating Wavelength, right? And then let's just make it easier for us, right? Let me just screenshot this so that I can just paste this right underneath so I don't continuously have to go back and forth, right? Just paste this here, this big, right? And normally in the exam, your exam sheet is going to be on a separate piece of paper, so you're not going to have this problem of, going back and forth through the pages, right? So what we first have to do is imagine the situation, right? You know that the second order maxima for the violet laser is a small 9.2 degrees smaller than the green light, right? So if you imagine on the double-slit experiment, obviously you're not gonna have to draw this yourself, but this is just for those who don't understand, right? You know that there is a violet laser, right? And then this violet laser, right, has a maximum. Let's say I'm just gonna draw a line in the middle because it's gonna get too messy. There's a maximum here, right? That's when n is equal to 0, when n is equal to 1, and when n is equal to 2, right? For violet. Okay, for green laser, what happens is, okay, there's the same thing, right? N is equal to 1. There is one that is n is equal to 2. And then there is n is equal to 3 here. No, n is equal to 2 here. My bad. Okay. And the difference between these two angles is 9.2 degrees, right? Let me just take a thinner pen. This is 9.2 degrees. That is the situation here. So if we find how much the violet light diffracts by, right? If we find this angle here, right? Let's call that some angle phi, right? If we find this phi, we can just add phi plus 9.2 degrees in order to get the total angle that the green laser diffracts by, right? This is going to be theta green, right? When n is equal to 2, right? So this is the given situation here. So, and then if we have the theta green, we should be able to calculate using the formula here, the wavelength of the green light. So let's go ahead, right? So let's try to find phi, right? Phi is going to be the angle for violet light when n is equal to 2. So we know that from part 1 that so we've from part 1 again we derived the relationship here, right? D is equal to n lambda sine theta n. So this implies for violet laser, for violet n is equal to 2, right? We can say sine theta 2, just rearranging here, right? So since n is equal to 2, it's going to be 2 lambda over d, right? Just simple rearrangement, right? So this must imply that theta 2, or otherwise phi, right? So just say phi is equal to theta 2 is going to be arc sine, and in this video I'm using arc sine and sine minus 1, right? They're the same thing, interchangeably, right? They accept both. D, right? So we know the wavelength for violet, we know the slit distance, right? So we can find the phi, right? And we can say, therefore, phi, no, therefore, theta green for n is equal to 2 must equal phi plus 9.2 degrees, right? Which is equal to arc sine of 2 lambda d plus 9.2 degrees here, right? And then for most of the cases, I recommend, solving for the answer later. But since already this value is in degrees, right? In this case, I would actually calculate the angle itself. So let's just say arc sine of 2 times, I remember it was 420 nanometers, was it? Yeah, 420 nanometers with this slit separation of 1.69 micrometers. Okay, 2 times 420 times 10 to the power of minus 9 over t was 1.69 times 10 to the power of minus 6. Right, if we punch this into the calculator, let's see what we get. So trig arc sine of 2 times 420 times 10 to the power of minus 9 over 1.69 times 10 to the power of 1.69 times 10 to the power of minus 6, which must equal plus 9.2 degrees, obviously, right? Which must equal 29.8 degrees plus 9.2 degrees. And this must equal, okay, just double checking my calculation, 39.0 degrees, right? And you might be, so if you haven't done rigorous significant figures yet, you might ask yourself, okay, we're adding 3 significant figure with 2 significant figure, right? But why are we getting 3 significant figure? And this is because for addition and subtraction, what matters is how many decimals, right, it has, and this is the least amount that we're going to take. So for instance here, it's the 10th decimal place that is the smallest, right, the smallest given value. So we're going to just write until the 10th, right, since this is uncertain value here. So we got 39 degrees, which is a nice whole number. We can assure ourselves, okay, we probably did not make a mistake, although it's not a good justification, but okay, it's a nice whole number, right? So we can assure ourselves, right? So we can use the same formula here. So again, we know d is equal to n lambda over sine theta n, right? So for green laser with n is equal to 2, we can say that lambda green is going to be d sine theta 2 over n, right? So we know that n is equal to 2. We'll just replace that with 2. And we can say, since d was 1.69 times 10 to the power minus 6 times sine of, we found 39.0 degrees, right? Over 2, which must equal 1.69. Trig, and let's say this is going to be sine of 39 degrees. So I get a 500 and, okay, I'll just write in scientific form first. 5.32 times 10 to the power minus 7 meters, which we can write 532 nanometers, right? So the question was, right, to find the wavelength for green light. So therefore, lambda green must be equal to 532 nanometers, right? And we can assure ourselves that this answer is probably correct because, as I said, when we're looking at the electromagnetic spectrum for a similar question earlier for double slit, not grating question, we found that for the green laser it was around 502 nanometers, right? So which is pretty similar, right? Which belongs between 500 and 600 nanometers. So we can assure ourselves, okay, it's probably correct. Okay, so let's finish with part C. I'm running out of space here, so I'll write on the right-hand side. So let me just draw a line so not to make it confusing. So explain whether the wavelength of the laser should be increased or decreased in order to increase the number of increase the number of possible maxima using the same grating. So we know that maxima is going to be given by, let's see, so let's just write C, and we can say should lambda increase or decrease. To increase n, right? Because n is the maximum number of possible, number of possible maximas, right? And since, let's just see, explain whether the, okay, so since we know the formula, right? We know from part 1 that d is equal to n lambda times sine theta n, right? So we know this relationship that lambda and n, right? We can say lambda is actually inversely proportional to, so we can actually say n, right? This implies that n is inversely proportional to 1 over lambda, right? So this shows that since we're just algebraically rearranging, and then since as d and d is a constant, right? As we're using the same grating, right? A constant. Therefore, lambda must decrease, right? Decrease in order for number of possible maximas to increase, right? As they are inversely proportional to each other. To each other. Right? This should be the end of this question here, right? Fairly simple, right? Although I would say question B might have been a little complicated if you didn't grasp the question, but overall, it's fairly simple. So, okay, so let's continue with the grating question, right? Now we know how to solve mostly grating question, what kind of question you're going to see in the exam, right? So let's apply your knowledge. Say that you send a white light through a grating. In other words, a continuous spectrum of light, right, visible light through the grating. What do you think you're going to observe? So pause the video here, have a think of it, maybe try to draw a diagram, right? And what you'll actually observe, seeing with this diagram here, is actually kind of what I guess Newton observed, right? That light actually diffracts, right? So in this case, I would say this is it's not a grating, right? It is a grating, but it's a mirror grating basically, right? So you're shooting the light through here and it's bouncing, and then you can see how different types of interferences form, and you can see how for the center node, right, center maxima, the light is just pure white light, whereas for others, right, you can see that the light is spread out, right? And this should be quite obvious because for the question that we did before, we learned that um, lambda, right? The wavelength lambda, it it depends, right? The angle that it diffracts at, right, is dependent on the lambda, right? That's what we learned in the previous question. So we know that bigger the wavelength, right, we know that it's gonna diffract more, right? And that's partially one of the Huygens-Fresnel principle, right? That we learned that the angle of diffraction is directly proportional, no, is equal to lambda over the aperture, right? And we know that so theta is directly proportional to lambda, which means that larger the wavelength, larger the diffraction angle is going to be. Since we know that red is around 700 nanometers, let's say, we know that blue is around maybe 450 nanometers, right? Or a bit more. Then yellow is somewhere in between, right? And then we must observe violet here, but maybe the camera didn't pick it up, right? So, right. So this is what we'll observe, right? And here it's just an explanation here of why red light diffracts more than bluish purplish light, right? Since red light has a larger wavelength compared to violet light, right? Violet light is maybe 400 nanometer and red is maybe 700 nanometers, correct? So this question is only showed up once in the past paper, which is going to be to do with thin film interference, right? And what you need to know for thin film interference is this formula here. And this is something you may have covered in maybe S4 or S5 long time ago. So I know for most people who are solving this question, right, in class, did not know how to solve it because they had to apply this formula and they didn't know what this formula was, right? So if you know, that's great. But if you don't, like most of us, right, I'll explain to you how to approach this question. So when you look at, for example, a bubble, right, on a, yeah, when you look at a bubble, right, when you look at maybe a CD, when you look at oil spill, right, you're gonna observe these weird rainbowish pattern. And you may have wondered why, right? Because if you have, for example, a bottle of that soapy liquid that you make the soap with, you don't have this color, right? If you look at a bottle of oil, you're not going to have this rainbow color. And the only time you'll actually observe this rainbow pattern is when there's a very thin layer of it, right? When the oil spills out to the floor, or when you put the bubble out, right? When you blow the bubble, right? You can observe these patterns. So how this happens is that basically, to explain it in a not too sophisticated and we're not trying to get too deep, because I think it's going to be diminishing return from here, because there was only one question in the baccalaureate, in the past baccalaureate in the 2021, that they gave this question. So how does it happen? So basically, right, there's a light coming. Obviously, it's like a double-slit experiment, right? And for instance, imagine that this is a CD, right? Light comes down, and then there's an internal reflection, and then this light sort of acts as a grating, basically, this thin surface, right? And okay, it's not like a slit, right? It's not multiple grating slits, but it can still act as a grating because it's going to send rays of light from internal reflection, right? So why is this formula important? Because you're going to be given the value for n, which is its refractive index, and then c, which is its speed of light in each medium, right? Then you may have heard, okay, can speed of light be different, right? Can speed of light change? And most people are going to say, no, speed of light is constant. That's what we learned, right? It's 2.9997 times 10 to the power of 8 meters per second. That's what most people learn. But that's only true in a vacuum. In reality, speed of light can change. And that is because in different mediums, a light has different refractive index. Okay, what do I mean? So for instance, let me just search up, right? Refractive index for diamond. Right? So we know that refractive index for diamond is 2.42. Okay. And we know that refractive index for vacuum is 1. That's how we define the constant, right? So say, okay, we'll just rearrange this formula here. We'll just say N2 C2 is equal to C1 N1, right? And say that 2 is diamond, and then 1 is vacuum, right? It's vacuum. So we can say that speed of light in diamond must equal C1 N1 over N2 times C1, right? We know that N1 is going to be 1, as I said. And then I said the refractive index for diamond was 2.42 times, so C1 for C1, right? Speed of light in vacuum. Let's just say, simplicity's sake, 3 significant figures. It's going to be around this value here. And if we punch this into the calculator, we're going to get 3 times 10 to the power of 8 over 2.42. 2.42. We must get we get around 1.24 times 10 to the power of 8 meters per second. And now this shows that actually light travels slower in vacuum compared to the light travels slower in diamond compared to vacuum, right? This is what this formula shows. So one other important notion that we're gonna need is that for light, when they change medium, right? For example, when it goes from vacuum to maybe some water or oil, right? We know that the speed of light changes. That's what we proved, right? And we know the formula C is equal to frequency times lambda, right? And also the wavelength change, but frequency for different medium, it always stays constant. That's important to know, right? Frequency is constant for both air and for both any medium, basically, when light changes different medium, right? So let's start with this question here. So this was in 2021 Baccalaureate, and I'll say this was quite an evil question because it is quite difficult in my opinion. But if you try it once, you should get it fairly often. And I think the difficult part was that if you didn't see this formula in the formula booklet, then you're basically screwed. Okay, if you want, you can pause the video here and then solve it first. Okay, assuming you try to attempt to solve it yourself, right? We'll go over it together. Okay, so what we do, right? We say, okay, say that this is question 1 on the baccalaureate and question 2 on the baccalaureate, right? We write Q2. Just take a thicker pen. And if you see exercise 12, it's because it's pulled from my teacher's sheet, right? And then, okay, it's Q2, and let's start with 1. Okay, what is 1? Show that the wavelength of the light in the plastic is 342 nanometers. Okay, I'm really tired. 343 nanometers, showing lambda in plastic is 343 nanometers, right? So we know that initially, right? We know lambda air is 532 nanometers, right? And we know this, and we know this is also a green laser, right? That's what we proved in the last question, that 532 was green laser. And we know that refractive index for plastic, right? N plastic is what was it, 1.55, right? 1.55, right? And refractive index does not have a unit, and we know that N air is just a constant. We just say 1.00, right? Technically, refractive index for air and vacuum are slightly different, but it's not by much, so we just say they're the same thing. So from formula booklet, we know this relation here, right? That N1, N2, N1 is equal to C1, C2, right? And then we can just say, okay, N plastic over N air must equal C air over C plastic, right? We're just replacing the symbols, fairly simple. And however, one problem is that, okay, we're given wavelength, but not speed, right? Speed of light in that medium. So what should we do? So we should just replace that with N plastic must equal N over N air must equal, you know that C is what? It's gonna be frequency, right? Frequency times lambda air and frequency times lambda plastic, right? And as I told you that frequency is constant for different mediums, so cancels out. So we get this new relation here that actually lambda plastic is equal to N air over N plastic, which is algebraic manipulation, times lambda air, right? And here we get that N air was 1.00 and plastic was 1.55, and then the wavelength was 532 nanometers, right? And if we put this into calculator, we should see that it's 343 nanometers. So it's gonna be 532 over 1.55. Correct? Yep, I put that right. And then we should get exactly 343 nanometers. Hence, proved. Right? We just write it here once more. Plastic is this value here. So let's continue with part 2. Okay, what does part 2 ask? The first order interference maximum is detected on a screen where the refracted light forms angle of alpha is 46 degrees as it emerges from plastic. Show that the corresponding angle of incidence is 28 degrees. Okay, what formula do we know with angles, right? We know the relation here, right? So what we're gonna do is, okay, so showing theta plastic is 28 degrees, right? Okay, so we'll just write that relation down. So sine alpha 1 over sine alpha 2 is equal to, we know sine alpha 1 over sine alpha 2 is equal to n2 n1, if I'm not mistaken. Yep, correct. So we know that angle, so we can just say, okay, just say sine alpha air over sine alpha plastic is equal to n plastic over n air, right? So we're trying to find the angle of plastic is 28 degrees. So we can just say, okay, we just simple algebraic manipulation. We can say alpha plastic must equal arc sine of n air over n plastic. Okay, let me improve my handwriting. Times okay, gonna be sine alpha air, right? So since we know all of these values, we can just say, okay, it's gonna be arc sine of n air, I told you it's 1.00, and plastic was 1.55, times sine alpha air, which is sine of 46 degrees, sine of 46 degrees is gonna equal, if we punch this into the calculator, trigonometry, arc sine, gonna equal basically 27.7 degrees, which is approximately 28 degrees, right? So, which is equal to theta plastic, right? Or we're just using alpha here, we're using theta here, but it is the same angle, so we can just stop here, right? Okay. So I'll write on this half, and normally on paper you should use as many pages as you need, right? Because you don't pay for your papers, so there is no point in trying to save space, right? You should take as much space as possible on the paper, right? Okay, the following diagram of a verb is an enlargement of the figure above. Okay, label diagram. Okay, so I'm just gonna screenshot this because I can, but whereas in reality you should draw this, right? And I don't want to just go back and forth on the paper, so that's why I am doing this. Okay, so on this figure, let's draw the slit path difference of the two emerging rays, right? So it's emerging, okay, it's going here, and we're just zooming in on this part here, basically, right? So we know that, okay, they travel the same distance here, right? Okay, that's true. So the path difference, right, should be, like the double slit experiment, should be when it's perpendicular here, because, oh, okay, it should be perpendicular here because the surface that is going to be projected on must be, I think, yeah. So this must be the path difference here, right? And it says copy the diagram, label the path difference. So this should be the path difference delta here, right? Between the two emerging rays. And we know also that we saw that this angle was, how much was it? Since this is 46 degrees, right? This must be 44 degrees. And this must be also 46 degrees, right? Since this two must add up to 90, right? So let's say that that's 46 degrees here. Okay, calculate the distance S between two adjacent slits on the DVD. So what are we trying to find? We're trying to find this distance here, right? So let's continue, right? Let's just say IV calculating S, right? That's what we're doing. So from part 3, we can observe that sine of 46 degrees is equal to, sine is opposite over hypotenuse, right? So it's going to be delta over S, right? That's what we're given. So also, what do we know? On the question, it says that light to first order interference maximum on the screen. So what does it mean if it's a first order interference? First order interference maximum, right? What does it mean? It means that since it is given first order interference maxima, we can confidently say that the phase difference should be just equal to lambda, right? Not any integer multiple, but just 1 times lambda, right? Therefore, we can just say slit difference just must equal lambda over sine of 46 degrees. Okay, what was lambda? We know that lambda was given at, since this is in air, so we must use the value of slit difference in air, which is 532 nanometers, right? It's going to be 532 nanometer over sine of 46 degrees, which must equal, okay, if we punch this into calculator, 532 divided by trigonometry 46, right? Okay, I get 730, okay, around 740 nanometers. So this should be, so therefore slit difference S must equal around 740 nanometers. And that is the end of this question here. So if you've been following along, that's great. And if you're able to solve this question yourself, that's great as well. So I know for now, right, for some of you might still not be sure, right? You might be thinking, oh, this is still hard for me. But one thing with physics, and especially the European Baccalaureate, is that every year the exam is, I would say, 75% same, and there's only the 25% element that changes every year. So the worst case scenario, right, you're gonna get at least, I'm sure, like 80%, right? If you solve at least most of the past papers, and if you remember how to solve them, you're gonna get at least, I'm telling you, 80 to 90%, right? The last 10% is just going to come down to if you make errors or not, if you catch yourself doing calculation mistakes, right? It's just going to come down to that and your luck. So, yeah, let's continue with the electromagnetic spectrum, right? And I don't know why I wrote diffraction grating here. Probably forgot to delete it after I copied the slide. So I'm sure in S6, right, if you took chemistry, I'm sorry if you didn't take chemistry and if you're somehow taking biology with physics, right, that about the Bohr's model of an atom, right? And if you remember this diagram here, maybe not this exact diagram, but about the emission spectra of atoms, right? And you know this diagram is only valid for hydrogen because that is the simplest atom, right? Just one electron, one proton. And you know that when electrons, right, they change energy levels from higher energy to lower energy, right? You know that they release a photon, right? They release electromagnetic wave to release energy, right? So what exactly is the electron doing in order to create that electromagnetic wave? You can pause the video, have a think of it. Okay, assuming you have tried to think of it, the answer is that electrons are being accelerated, right? They're being accelerated from here to down here, perhaps, right? I know this isn't like 100% accurate to say, right? But I think this gives you a good intuition of how electromagnetic waves are created, that they're being accelerated, and this acceleration causes the electron losing energy to release photon, right? Because energy is neither destroyed or created, right? They must be transferred, right? If electron goes for higher energy to lower energy, right? It can't just hold on to the energy in the lower energy, right? It needs to release it somehow, and it releases through the medium of electromagnetic wave, right? Okay, this is another important definition to know, which is that electromagnetic waves in general are produced by the acceleration of charge, such as an electron. We say in general because there are cases that is not, but in our level, we only have to know that it is just produced by an acceleration of a charge. And just for sake of having fun, let's have a look at like a case where it is not created by the acceleration of an electron. So there are many cases, one of them being a nuclear decay. And maybe you learned this end of S5 when you're doing nuclear chemistry, that there is a gamma decay, basically, the uh, where the nucleus releases energy through photons, right? Through here, gamma decay, right? They release just gamma rays, right? Gamma rays, and you know that gamma rays is also electromagnetic wave, right? It is the strongest, highest energy, right? Another one, or how electromagnetic wave is created, is through matter, antimatter annihilation, right? And okay, this is obviously very advanced quantum physics, right? I don't know what field this is. Probably quantum physics, I'm guessing, right? But when matter and antimatter they combine, right? They release their entire energy through annihilation, and I'm sure I think this is where E is equal to mc squared is related, right? How mass can be turned into energy, basically, right? And then lastly, there's black body radiation, right? And if you looked at, during the COVID times, if you look at the thermal cameras, right, and how people with fever, their forehead is red, for example, and then if you look at, I don't know, a cold place, it's blue, right, on that camera, right? That is actually the infrared camera, infrared light, right? Infrared light camera. And what black body radiation means is that any body that is above 0 kelvins, right? Above the absolute zero, releases some sort of electromagnetic radiation, right? And you know that, okay, when you heat up metal, right, it starts showing red or like glowing white, right? So this is a phenomena where, okay, maybe metal at room temperature is releasing infrared light, and perhaps the infrared spectrum. That's why we can't see room temperature metal showing light at room temperature, right? Whereas when you heat up the metal, it starts releasing in the visible spectrum, and that is why, right? And also we can create electromagnetic waves in a non-natural way, basically, right? And depends what you define as natural, non-natural, but we can do this through an antenna, right? Your phone has antenna, your computer has antenna, the world is filled with Wi-Fi and, you know, the radio waves, right? So how are actually electromagnetic waves created, right? And we learned that they're created through an acceleration of a charge, right? And if you think of a copper wire, right, of how electricity is flowing in the copper wire, there is actually electron being accelerated in the wire itself, right? So if we apply on a wire an alternating current, in other words, current that is uh, making the electrons go back and forth, right? It means that uh, the electron is creating electromagnetic wave, right? Then we can actually define what the wavelength should be by changing the frequency of this alternating source, right? We can say, okay, do we want a higher frequency, right? How we want a higher frequency electromagnetic wave, so we're just gonna apply a higher frequency on the alternating current, right? So let's read this together. Electromagnetic waves can be produced by a variety of devices, but most common is probably an antenna. An AC voltage is applied to the antenna, which leads to one side of the antenna accumulating positive charges, right? Which is potential difference, right? And the other side accumulating negative charges, right? The repartition of charges change within time, with time leading an alternating electric field being generated. The wavelength of the electric field is twice the length of the antenna, so the length of the antenna can be tuned to produce the field in a desired wavelength. Similarly, as the charges move through the antenna, the current I is equal to dq over dt is maximum in the middle of the antenna. The current variation creates a magnetic field, which is perpendicular to the plane of the paper. Okay, a mouthful, but I think it's quite intuitive what's trying to explain with the diagrams here as well. That, okay, we can actually create different wavelengths through altering how big the antenna is as well, right? And generally, we said that it is electric field is twice the length of the antenna. So we can just formulate a simple equation here that length of antenna must be half of wavelength, right? If we desire to produce, let's say, a 5-meter wavelength, we can just say, okay, we need an antenna that is twice as large, right? So it must be, so actually, no. Like if we want to produce 5-meter wavelength, we say that length of antenna can be just 2.5 meters, right? Because it's half. Okay, so what is an electromagnetic wave, right? I think the name itself gives a quite an obvious answer, right? Electromagnetic, meaning, okay, there's an electro component and there's a magnetic component, right? And electromagnetic wave, right, if you remember from S6, the different types of waves, is a transverse wave because the motion of the wave is the motion of oscillation is perpendicular to the motion of its direction of travel, right? The electromagnetic wave, oh my bad, the electromagnetic wave is traveling to this way, whereas the electric field and the magnetic field is directly perpendicular to the direction of travel, meaning it's a transverse wave, right? And you might be asked to provide definition of transverse wave, right? I think it was in one of the past papers, right? So, and I mentioned this as well in the introduction video on the week 0 as well. And as you can see, right, electromagnetic wave is composed of two fields, right? Electric and magnetic field, right? And that's why they can be considered as quote unquote waves, right? And don't overthink too much about, okay, these are actually photons. Are they oscillating back and forth? How does it work, right? Don't think too much about it. We're not quantum physicists yet, right? And even when we study quantum physics, we don't go in that deep. So that is what electromagnetic wave is, right? And you know that if you recall the electromagnetic wave spectrum, you should recall that it goes from radio, micro, infrared, visible, UV, X-ray, and gamma. That should be the order that you should remember the electromagnetic wavelength as. Okay, which part of the electromagnetic wave is dangerous? I'll let you a couple seconds to think of it, and yeah. So actually, contrary to many people's beliefs, right? It's from ultraviolet where the light becomes actually dangerous. And the reason why it is dangerous is because ultraviolet light, X-ray, and gamma rays are ionizing. This is a key word when you're asked to provide the dangers of, um, for example, the electromagnetic wave. Why is X-ray dangerous? Because it is an ionizing electromagnetic wave. Okay, if you recall from S6, what is ionization energy? It is the energy needed to take away one electron from 1 mole of gaseous atom, right? I think that is the definition of an of ionization energy, right? In other words, right, ionizing rays or ionizing electromagnetic waves means that it can take out an electron from an atom, right? And for example, if you imagine a DNA molecule, right? DNA is obviously everything's made of electromagnetic, everything's made of atoms, right? And then imagine you shoot UV light or X-ray on this DNA molecule, and you take out some electrons, and some kind of weird bond is formed, right? And this alteration of the DNA is what causes cancer, and especially, for example, skin cancer is caused through ultraviolet light, and that's why you shouldn't go to the sun without applying sunscreen, which helps create the barrier between your skin and the ultraviolet light, right? So as you can see, it's from ultraviolet light where the photons or the light becomes ionizing, right? As I wrote here, broken bonds can cause DNA cells to mutate and thus form cancer. But you might ask, okay, actually microwaves, right? If I put my food into microwave, they heat up, right? And they become sometimes really, really hot, right? It doesn't sound pleasant if you go into the microwave oven and then turn it on, right? So in this context, yes, microwave is dangerous, right? However, it is only dangerous not because it's ionizing, but because microwaves heat up water molecule. And I'm not gonna give you the technical details of um, why microwaves heat up water molecule, but I'll try to give you an intuition here, right? And say that you're given the information that the microwaves have the perfect resonance with water molecules, right? Some sort of microwave, right? And they vibrate the water molecules, right? They make it go up and down, for instance, right? Okay, if you recall the kinetic theory of matter from chemistry, right? I think this is a lot related to chemistry here, right? You know that the kinetic energy is directly proportional to the absolute temperature in kelvins, right? So we see that, okay, higher the kinetic energy of the molecules, higher the temperature is going to be, right? And if you oscillate the water molecules enough using the microwave, right, you're going to heat up the food because you're increasing the kinetic energy of the water molecules, right? So basically, on a surface level, what you should know is that water molecules, right, they vibrate in the microwave spectrum, right? Not the entire spectrum, but a very specific wavelength in that spectrum. Because to be honest, like your 5G phone, your Bluetooth, right? All these electromagnetic waves, right? They are also in the microwave spectrum. Right? They're not in the radio spectrum, they're in the microwave spectrum. And for example, these AirPods, they're not like frying my brain, right? As some people say, oh, like these people who don't take science, they think that oh yeah, these headphones are gonna fry your brain out, you know. But in reality, right, this room is filled with Wi-Fi, right, and the world is filled with radio waves, right? So technically, right, yeah, sure, these are emitting microwaves, but so is your phone, so is your router, right? Everything's emitting microwaves, right? So it's not dangerous, microwaves, but specific wavelength of microwave is dangerous because they cause the water molecules to oscillate, heating up things, right? So only in high doses is microwave dangerous. And since they're non-ionizing, they can't cause cancer, for instance, right? So I was gonna do this exercise here, but I think I explained it enough uh, how electromagnetic wave can be produced through an antenna, right? And I also mentioned this part of how 5G mobile phone is actually belongs to the microwave spectrum, right? So I'll leave this as an exercise to the viewers, and yeah. So I was actually looking through the syllabus once again after I thought I finished making the after I thought I finished making the slides, but I read about this part here, right? Historical experience to measure the speed of light, right? For example, these ones. And these ones should be covered in class as well, but in our class we didn't cover. So I'm gonna very briefly just touch on them, like 1 minute per topic here. So, uh, probably like 2 or 3 hours ago, you learned about the history of light, right? I taught you about the history of light. And I taught you about Newton, Thomas Young, James Maxwell, Albert Einstein, and about the Higgs field that they're doing in CERN, right? So these are the two key figures that we're going to introduce, which is Ole Rømer, I'm probably pronouncing that wrong, and Hippolyte Fizeau, right? I'm going to introduce two new key figures of discovery of light. Okay, the first one, Ole Rømer. What he proved is that speed of light is actually infinite. Not infinite, but finite, basically. Okay, speed of light has a maximum speed, basically. Then how he proved this is he tracked one of the moons on Jupiter, and he was looking at the eclipse of the moon, right? And he realized that when Earth is traveling towards versus Earth is traveling away from Jupiter, that these eclipse, the speed of the eclipse, I don't fully understand either, but the speed of eclipse changed somehow. And through this, he proved and he deduced that the speed of light takes around 22 minutes, right, to cross Earth's orbit. And he calculated that, okay, this should take around 2.2 times 10 to the power of 8 meters per second, right? And this, right, is surprisingly accurate. Like, it's maybe 30-40%, right, different to our actual speed, which is around 3.0 times 10 to the power of 8 meters per second. So surprisingly accurate, and he proved that, okay, light has a finite speed, right? The Fizeau apparatus, right, we saw the Hippolyte of Fizeau, right? He's another scientist here, and he measured the speed of light within 10% accuracy. So I guess a bit more accurate than this, but 200 years later, right? So this was historically significant as it was the first instance to measure speed of light on Earth, right? Before that, people are measuring speed of light in cosmos, right? Looking through telescopes. Next one is interferometry, and you can kind of deduce by its name that it's something to do with interference phenomena that we are studying, right? So what this person did is he shot a laser through a half transparent mirror, as you can see here. And then there's a movable mirror here, and there's a fixed mirror here. And by moving the mirror, we can alter the pattern on the screen. And through this alteration, he proved that speed of light is constant in all direction, basically, right? And he wanted to prove that it was not, but it was. So he didn't prove his thesis, but he proved another person's thesis, basically. The last one is Fresnel experiment, and Fresnel mirror experiment proved that interference is not only caused by the slit experiment, but also through reflection, right? So yeah, that's what it proved. At Fresnel, he proved that light can be diffracted through mirrors as well, right? So these are the learning objectives, right? So we learned about the Huygens-Fresnel principle. We talked about the double-slit experiment, right? We talked about how we can draw it and how it is carried out. And we learned about how to derive these formulas. We learned that accelerating a charge causes electromagnetic wave. We learned about how electric and magnetic fields are perpendicular to each other, right? We learned about comparing the electromagnetic waves, and we learned about this, right, many times, comparing different wavelengths, right? And we learned about its application, right? Wi-Fi, radio waves, right? And yeah, I think I covered most of it, if not even more than the syllabus. So hopefully by the end of this video, you should be able to have a confident grasp on this topic here. And you can have a read out here to see if you can do everything, right? And that should be the end of the video. But one last thing, which I think I forgot to mention in the double-slit experiment is how Thomas Young carried out his double-slit experiment. As I mentioned, he didn't have a laser, but he somehow managed to do the double-slit experiment. And the way he did it was basically, right, he only had access to sunlight. So he used the sunlight, right? And then he shot it through a single slit, right, to produce a coherent single light. And then this single slit, he passed it through a double slit so that he knew that this source of light was coherent, right? They had the same phase and the same frequency, right? So, and then, right, there's the double slit experiment here. They interfere and he observed the patterns, right? So this is what I like to add just to give you a sense of how Thomas Young did it, although lasers were invented much later, right? So that's the end of this video. And after I'm done making the 7-part, 8-part series, I think and then I'm gonna cover each of the baccalaureate papers. I'm gonna solve them through. I'm gonna do a walkthrough. So by the time maybe you're watching this, all the videos should be uploaded. You can continue watching the next one, or what I recommend doing is just